I'm crazy, 'cause I'm so in love with you. And I know that you don't love me the way that I love you.
your home for the smoothest jazz. Smoothjazz.com, Global Radio. Gold record keyboardist, producer, film composer, music director, and songwriter Charles A. Kelly celebrates the release of You're Not Alone on Intervision Records. A world-class collection of uplifting, spiritually minded melodies featuring sparkling piano magic. Find You're Not Alone now in the smoothjazz.com listening loft and everywhere you source your music. Meet the artist on social media at Charles A. Kelly Music. The follow-up to his successful Sing-a-Song release, Germany's Amandus, returns with the full EP, Her Love. Keyboardist and composer Michael Amandus Quast delivers vibrant, smooth, and seductive tunes that inspire and are inspired by love.
She wanna show me how to love now. She wanna give me all her love now. She wanna be my only love now. I wanna be her only love now.
Her Love is available in the Smooth Listening Loft and streaming all over the world. Meet the composer and keyboardist at amandusmusic.com. Acclaimed recording artist Spontaneous Groovin' Combustion returns with this infectious and uplifting new track, Name Dropper. And speaking of dropping names, the ensemble's Warren A. Keller is featured on flute. With Blake Aaron showcased on guitar. Name Dropper, available now in the smoothjazz.com listening loft and everywhere you find the superstars of your soundtrack. Dig in deeper at spontaneousgroovincombustion.com.
Um,
Als er twee mensen lopen, weet die camera niet wie dat hij moet volgen.
ja.
Dus eigenlijk moet je hier alleen staan en dan als er geen enkelheid is, dan pakt die over. Want dan is die camera.
Nee, geen probleem. Oké.
En dan moet je officieel starten als.
Ja,
Nog eens aan Benny vragen of dat dan nog een licht moet geven, maar ik denk dat die klaar staat.
ja, het staat nog niet live. Dus.
Ja, ergens aan het wachten, ja, oké.
Maar ik denk dat het met aan het veranderen is nu, of dat het met aan het live zetten is.
Ja, is nu even image aan het helpen.
Okay, welcome everyone. I'm Steven, and this is the second game conference, the Geometric Algebra mini event. And it's great to see so many people here. I hope you will have a fun time. You should think of the following 3 days as sort of a boot camp or a bath, if you wish. And it's actually quite a challenge that we have here. We're basically trying to explain a rather intricate and detailed branch of mathematics in just 3 days. And so before we begin, I want to sort of make you aware of what to expect from that, because for sure, at some point, you're going to feel a little bit overwhelmed. And that's absolutely normal. Mathematics is not something that you can explain in a simple linear way. It's more of a web, a spider web. That's actually sort of the underlying theme. And so it is necessarily so that we will explore this web in one direction and then go back, visit another branch, and so on. And in order for the entire thing to make sense, you will need a few of these branches. So as you move along, you will be lost. The bit of information that you need to understand is in the next slide or in the next talk. So the best thing to do really with these 3 days is take it all in. Even the stuff, we have some professors from Cambridge talking about physics. Of course, you want to do that because it's a professor of Cambridge talking about physics. It's really fun. But even if you're not a physicist, you want to do that because it will connect back, because everything in geometric algebra uses the exact same mathematics. And that makes it exceptional and different. Normally, when you go to physics, you'll have to learn tensors for general relativity. You'll have to learn all types of other mathematical methods to do all types of other things. And geometric algebra pulls it all together. So once you get this basic understanding, you will be able to follow these talks. Of course, not in all the details, but in more than enough detail to connect this back. And at some point in your career as a game developer, you will look back and you will go, oh, really great that I did that physics stuff.
So then I get a bivector here, and I also have the opposite product of E2 times E1, and that gives me the negative version of that. I'm getting some feedback. All right, so we have those elements first, and then I can do the same thing with the other basis vectors, right? So I multiply, for example, E1 by E2, and that is a new element I haven't seen before as well. Oh, sorry, E1 by E3. The same here with E2 by E3. So I have discovered all these bivector quantities, so I will add them to my table, right? So I add them as column headers here and as the row headers. And now I can start multiplying those things together as well. So if I do E1 by E2, by E12, then I get an E2, right? By the fact that E1 squares to plus 1. And the same now for E1 times E31, right? And now I have to be careful with the anti-commutation rule here, so that I have to swap the order, and that gives me an extra minus sign. And now I get an interesting one. I multiply E1 by E23. And that's something I haven't seen before yet. Nothing collapses because there's no identical vectors touching each other. So I just get E123. And that's a new element we haven't seen before. And so I have to add that to my table, right? I have this new entry, which is called the pseudo-scalar, E123. And now I can continue completing the table. So if we take, for example, a bivector by itself, we get -1. I get the same for all 3 bivectors. And if you work it out nicely, following just the simple rules that Steven has talked about, then E123 by E123 also gives a -1. And so now you can complete this whole table. And this is called a Cayley table. And actually, if you are trying to implement your own version of the algebra, then you would have to implement this table. This is how the different elements will interact. All right. But besides a Python user, I'm also a physicist, so I would also like to take some time to lay some foundation for the physicists, because we will have some talks relating to physics later on. And the most interesting algebra there is the space-time algebra, which is called STA for short. And that's the algebra R13. So we have 1 basis vector which squares to +1 and 3 that square to -1. And for a physicist, we don't write, as physicists, the E notation. We instead use the Dirac gamma matrices. But really, those gamma matrices are the basis vectors of our geometric algebra. So it's just a for us now, it's just a notational trick. We switch what we used to call the EI guys that Steven talked about to gamma I. And for a physicist, these are those matrices in what's called the Dirac basis. And as a physicist, we really grow up with this. And we are aware that they behave like vectors, but GA really allows you to really write it as a vector. So that's this mapping I have on the right here. That's how we relabel them. So actually, we start counting from 0 for the time dimension, and then 1, 2, 3 for the spatial dimensions. And there's another neat trick that we need to know, and that's something called the Pauli matrices. So those are these 3 matrices down here. That's also something very well known in physics, and it's related to spin. But the Pauli matrices are just the basis vectors of 3-dimensional space. So we also have those in our GA as basis vectors. And the mapping we use between the two is that the ith Pauli matrix is the ith gamma matrix times gamma naught. And so these are for the 3 spatial basis vectors. But by this trick, these are living in the even subalgebra. So for example, sigma 1 is E23. So because we take the product of 2 of the gammas to make the sigmas, those are actually bivectors. And The way we use these is to generate the full Lorentz group. So those are rotations and rotations in the time direction, which are technically called boosts. So there's this mapping from the basis vectors of space-time to the basis vectors of space is formally known as an isomorphism. So we have that the spatial algebra is isomorphic to the even algebra of space-time. Now, why am I telling you all of this? I just want to give you a quick preview of the kind of power that we have in geometric algebra to simplify things. Like Steven was talking about, how many equations can become one equation. And the great example there is the Maxwell equation, singular. So in GA, the Maxwell equation is the gradient of a field F is equal to a source term. And this F is called the field strength tensor, and it combines the electric and magnetic fields into one bivector. And this, so the gradient operator, that's the derivative in all the different space and time directions. And a source term is just a vector quantity which represents, for example, a point source sitting somewhere in space-time. And to prove to you that we get all the usual Maxwell equations from this, we use something called the space-time split. So that's this idea that by multiplying with a gamma 0, we can go from the full space-time to just the spatial part. And so if I take, for example, my source term j, and I multiply it with a gamma naught, then we know from the rule that Steven talked about, which only applies for vectors usually, that j times gamma naught is j dot gamma naught plus j wedge gamma naught. And this is a scalar quantity and a bivector quantity. And the scalar has a name in physics, and that's the charge density, rho. And the wedge part, j wedge gamma naught, that is the charge part here, j. And I can do the same thing for the gradient operator. So for the gradient operator, I take the dot and the wedge part. The dot part is the time derivative, the scalar part. And the wedge part is what we call the usual gradient, which you might be familiar with, the derivative in 3 dimensions. And that has this NAMBLA notation. So what I can do with this is I first start from the Maxwell equation, then I multiply with gamma naught on the left, on both sides. And then I apply these two simplifications, or actually, well, you could say verbosifications. And I apply a gamma naught on the partial operator, so that becomes a derivative with respect to time, plus the nabla operator, the spatial derivative. And my F part, I write that as the electric field plus the magnetic field. And on the right-hand side, I write my charge density and my current, J. And then I can expand this out. So I just work out the brackets. And now I have here, for example, the gradient of the electric field, and I have also a gradient of the magnetic field. But for those, we have the rules again that those decompose into a dot product and a cross product normally, right? So that becomes the gradient of the electric field, for example, is the divergence and the curl, let's say. And I do that for both of these. So it's only becoming more verbose, but bear with me. So what we will do now is we start to equate these quantities grade by grade. So for example, the divergence of the electric field, that's a scalar. And rho on the right-hand side was also a scalar. So I equate those two together. And now similarly, for the other quantities, I will just start to equate them grade by grade. So for example, the time derivative of the electric field, that's a vector. I'm looking at it in space, not in space-time. So the partial derivative is a vector. And the curl of the magnetic field, with this I in front of it, which is the pseudoscalar in the space, that's a vector quantity. So I just collect together all the vectors as well, then I get this equation. I do the same for the bivector parts, equating those together. And then lastly, I have a pseudo-scalar valued part here, because the I is the pseudo-scalar. And so I get these 4 equations. And these are traditionally known as the Maxwell equations. If you look at any physics textbook for the Maxwell equations, then you will find these 4. With actually the slight modification, of course, that instead of a wedge product, we write a cross product here. So actually in GA, these 4 Maxwell equations become a single Maxwell equation. And this is the most compact form of the Maxwell equations that we know about. And for comparison, in tensor analysis, we can get pretty close, but then we still need 2 equations. And so for the scalar part, we have this typical equation, and for the wedge part, which should be equal to 0, we have this Bianchi identities. So this is much more compact than anything else out there. So that's just as a nice example of the kind of simplifications that GA can offer us. All right, and that brings me back to the original speaker, Steven.
All right. So SDA, that's really for the physicists. So if that was above your pay grade, that's absolutely fine. Don't worry. There are some people in the room who are used to working with those things, and hopefully they had their little aha moment. So now we're back to the graphics programmers and game developers. So the algebra that we will be talking about in the next talk is called the plane-based geometric algebra, and some people even they're calling it the projective geometric algebra. And that is actually a geometric algebra that is the one that we really want as graphicians. And the illustration that you're looking at right here shows you that this algebra actually comes in 3 different flavors, right? When we're looking at the picture the way it is now, we have our eye at the origin. But when we move the camera away, we see that those things that we thought were lines, they actually turn out to be planes through your eye, right? And that's an idea that's actually going to come back. So if you turn the plane all the way flat, then it looks just like a line, right? And this was Klein's big revelation. He realized that when you have lines like this, and you actually use planes through your eye to do your calculations, then it doesn't just work for flat space. It also works for spherical space. It also works for hyperbolic space. And so this was a defining moment in mathematics. Klein's Erlangen program, it is called, is when people realized that there was more than just Euclidean flat space geometry, and Klein realized how to unify all of these geometries. The model that we will be using to do geometry today is exactly this model. We will only be doing the flat part, right? But when you do the flat part, you get the other ones for free. So I do really want to stress that. You get those for free. You want to make a game that plays in hyperbolic space. Well, that's just as easy as making one that's in flat space. Or if you want one that's on the surface of a 3-sphere in 4 dimensions, that's just as easy. It's exactly the same thing. You would be using exactly the same formulas, ideas, and concepts. So the 3 algebras that are in this family are these algebras. So for flat space, we're going to use 3 positive generators, and then the extra dimension, the projective dimension, is going to be one of those 0 squaring vectors. That will give us flat space. If for the extra dimension instead we take a positive square, because square 2 plus 1, then we'll be on the surface of a sphere. And if we take a negative one, then we will get hyperbolic space. Notice that that last one, R31, is actually also very similar to the space-time algebra that we were just talking about. What will this algebra actually allow us to do? Well, it'll give us much less formulas, right? That's what we wanted. We want to simplify doing things with geometry. We want to be able to work with points, lines, and planes directly, right? So the geometric product will actually represent composition. So if you have a reflection and you multiply it with the geometric product with a rotation, then you'll get a new object which will be the composition of the two. It'll be the reflection followed by the rotation. You can multiply in some translations and other things. And that's what the geometric product will do. The wedge product or the outer product, you know, the highest grade part of the geometric product, that is going to be our intersection operator. So that's your ray tracing tool. You can take two planes, you can take their wedge product, and that will represent the line where they intersect. If you take a line and a plane and you take the wedge product, it will represent the point where they intersect. So whatever you want to intersect, that just became trivial, right? Right now in your code, when you intersect something with something else, one, it is very specific for the types that you're intersecting with, and two, it's definitely more than one character, right? You're going to have a bunch of code there. You're going to be calculating coefficients and coordinates, and you have exception cases and check epsilon values. Am I too shallow to the plane to consider an intersection point and so on? All that goes away. Intersecting two things is just going to be calculating that outer product. So as far as simplification goes, this is a couple of pages of code that we have literally replaced by a single operator that is easy to calculate and easy to implement and extremely efficient. No exception cases. Similarly, one of the other products is going to be used to join elements. So you have 2 points and you need to figure out the equation of the line through those 2 points. That's just a single product, right? You will just do, oh, that's a join, we call it join. The other one we call meet. So you'll just go, oh, you just join the 2 points together, and that'll give you a multivector that represents the line. And if you join in a third point, you'll get a multivector that represents the plane. And then you can wedge it with another line to find an intersection and so on. So you can, all of the things you do in geometry will translate directly to these very, very simple expressions. So that join, that's another couple of pages of code where you now have code, oh yes, create a line from 2 points. Oh, and I also have one, create a line from a point and a direction. Oh, and you have a whole bunch of these things written out today in your code, and you're not the only one. Everybody is still doing lots of these things in the classical way. Things are changing. We had 3 talks about this algebra at the Game Developer Conference this year, and we actually have a bonus speaker in the afternoon, which is Hamish here, who was talking at the Game Developer Conference this year, and is doing part of that talk again. So you definitely want to hear that. It'll also be about this same algebra. Another example of the simplification we get and of a type of geometry operator that we need is when we want to project a point on a line or a point on a plane or a line on a point or a plane on a line or a plane on a point or anything on anything. It's always going to be the same formula. It's a dot product and a geometric product. So as far as simplification goes, for us as graphics programmers, there really is a lot to be gained. Martin did the Maxwell equations from 4 equations to 1. With just what I've written here, we've gone from about 50 or 60 equations to 4. Because it's so really, we are going to be so lazy, you have no idea. So in this PGA algebra, what we do is we model transformations as compositions of reflections. We'll go into a lot more detail on that in the next time talk because it's fundamental to truly understanding what's going on. And we are actually going to look at elements as being invariants of these transformations. And it'll turn out to be an extremely natural language to describe the geometry of points, lines, planes, volumes, and so on. In the talk, the first talk in the afternoon, which is by my favorite professor of all time, Joan Lazenby, she will actually take that idea of reflecting in planes and lines, and she will bend those planes and bend those lines in your minds, and that will actually get you the conformal group. So in the first talk, we'll be doing Euclidean geometry, where the transformations all preserve distances. Every distance stays the same. And then when Joan takes over, it's the conformal group, and that's the group of angle-preserving transformations. So that means you get scaling. In the first part, you don't get scaling, because if you scale, then distances don't change, stay the same. But if you scale, angles do stay the same, so they are conformal transformations, and that's what Joan will be talking about. She will also have some cool examples on inverse kinematics, and she is actually behind one of the most famous inverse kinematics algorithms out there, which is called Fabric. And then later this afternoon, we have Chris Doran speaking. Chris Doran is the guy who did the Enlighten global illumination system that first came out in the Frostbite engine, I think, but it was also on several generations of PlayStation, and it's only recently been replaced by Lumen. And he will be talking about optimizing geometric algebra implementations with some specific graphics examples also, and that's the last talk of the day. All right, so very small recap, and I know you guys are all probably flooded, so we'll have a 10-minute break after this before we start the next talk. Remember that there were only these two simple calculation rules, and this was the first hour. If you give yourself some time, you will find it just as obvious as I do. It's very, very simple. You then had a bunch of products that basically were all the same thing, and you just picked out whatever you thought was interesting. So I tried to think of a good mnemonic for you guys so that you could remember all this, but I couldn't really come up with anything. So I just have a bunch of random letters. So the first random letter here is that it is linear, right? I could say it's vector spaces, but when I say that, you all think arrows, and we're going to go way beyond arrows. We're going to do much more than arrows. So it's all about linear spaces. They are graded. You don't just have vectors, but you get all these higher grade elements, right? So that would be the bivectors, the trivectors, the quad vectors, yeah? and then some, right? So I don't know how you're going to remember that, but there you have it. Good. So the next talk is going to be me again. I apologize. You will then not hear me again until Friday, because on Friday we are going to do a workshop where we will do this from scratch. Right? This is going to be maybe, I think, 25 lines of code. And I've structured it in 6 exercises. And we will be animating that spider. We will be doing the inverse kinematics. We will be doing the path planning. It's a guided exercise. And it will use all of these cool formulas and all of these cool operators. So until Friday, you guys are going to be so overloaded, but I hope you hang in there. I hope you realize the value of being here in person. I mean, we have people from Cambridge, we have Leo Dos from the University of Amsterdam talking. You could watch the video, but that's not the same thing. You have to hear Leo, you have to feel him, you have to smell him. So full sensory perception, and if you don't understand it right away, don't worry, you still heard it, your brain got it, you are much better than OpenAI at training on live data. I mean, they can't do it at all. It takes some months to learn stuff, and then GPT doesn't know anything about geometric algebra, by the way. Okay. So thanks, guys, and I'll see all of you for the rest of the week. So we'll take a 10-minute break because apparently there was a problem with the audio on the stream. We're going to try to fix that, and then we'll get back and we'll dive into geometry. There's going to be much less algebra. It's going to be pictures and animations from now on. Okay, so see you in a short while. Thanks.
know whether we need for the recording. It's a bit bleak here.
It is, yeah. That would make it, especially over
You
that
have
side.
white and black or black and white?
I have white. I have black on white. With this, it's kind of better.
uitloop hebben.
Ja. Mentionen even. Of... Ja, ja. Wait. Ah, maar ja, dat gaat niet helpen als ik dat daar zet. Als we gewoon naar bij Victor gaan, op de frontpage staat er een game link en daar staat de stream. Gewoon bij Victor.net. Ja, maar als ze de stream niet hebben, kunnen ze dat niet zien, hè? All right. Okay, so now that we have all of the boring algebra stuff behind us, sort of, we can get focused on what we really want to do, which is we want to do geometry, and that's exactly what I'll talk about in this first talk. So we are going to quickly recap what we just did actually, so that it's self-contained in the video. That's only going to take 1 minute. And then we are going to introduce some ideas that we will need to understand how to do geometry with points, lines, and planes. We will determine what makes an operator and an element a geometric element. We will get to sort of a definition and an ID for that. And then we will build a tool bag of operators that will meet these requirements, and we'll implement that with geometric numbers, and then we'll talk about something that will pop up called geometric gauges, and we'll do some exercises with that too. So, quick recap of what we just did. The algebra that we will use for 3D geometry, for your gaming applications, for your graphics applications, is mostly going to be this algebra R301. So we have these 3 generators that square to +1. We have 1 generator that squares to 0. Any vector can now be written as a linear combination of generators. Instead of writing x, y, z, w, like we do today in computer graphics, we would write something similar to xe1, ye2, ze3, plus w, e0. We still have those 2 basic rules that work for any geometric algebra. Because we're saying here it squares to 1, -1, or 0, but we're not using any generators that square to -1. So obviously, each generator squares to its own square, right? But with these rules, you can do all of the geometric algebras, not just the one we're doing today. If we work this out for R301, you will have if you were to make the Cayley table, you have 1 scalar element, obviously. You have 4 generating vectors. You get 6 bivectors, the number of ways you can combine 2 elements out of 4. And you get 4 trivectors, and you get 1 quad vector, which then has all of the 4 basis vectors in it, which we call the pseudoscalar. A general multivector is a sum of k vectors. That's just basically saying we can add all these things together and treat them as a sum, and it'll always distribute out, and you can easily do that. Then we have all of these products. We're not going to go over that again. We're still skipping lots of details, right? I'm absolutely not lying if I say that these are the 2 axioms from which everything comes, but there are so many ideas that flow out of this that we haven't even talked about yet. For example, a reverse. So if you have E12, then E21 is the reverse. So if E12 is going to be 2 reflections, a reflection in E1 and a reflection in E2, then E21 is going to be the same reflections in the other order. And we'll have a way to do that algebraically. It'll be super easy. You change some minus signs and you're done. I haven't explained that yet. I haven't explained that the inverses are easy, although you guys should have figured that out yourself, right? Because we said that we have these elements that square 2 plus 1. That means they are their own inverse, right? If you multiply something with its inverse, you get 1. In this case, you multiply a vector with itself, you get 1. So this vector is its own inverse. So dividing is not something scary at all. I mean, it's the same as multiplying, literally, for these vectors. And if you have those guys that square to -1, you'll still have an easy inverse. It'll just be minus the same element. If you have guys that square to 0, you don't have an inverse, right? You can't do that. You can't divide by 0. But you're all programmers, you know that. So the question that we'll focus on is how are we going to use all this to do geometry? And since I'm not going to assume that many of you have done a lot of abstract mathematics or have even seen different types of geometry, I sort of want to give you 2 examples so that you understand that there are different geometries out there. There is a geometry for almost anything you can think of. And there are also different ways to define a geometry, to describe how your geometry works. So one really basic way that people have been using for a long time to do geometry is you start from a set of elements. And of course, Euclid's classic example is you start from a set of points or set of lines and so on. And you have a distance function. So you have this ID of a distance. And that's basically all you need to define a geometry. Another way to define a geometry, and that's actually the way that Klein does it, is to say, if you start from the elements and the distance function, you will ask questions like, what can I do that preserves the distance? Oh, you can move stuff around, you can rotate stuff around, you can reflect stuff. They all preserve the distance. Klein actually turns it around. He starts from the transformations. He says, oh, if you do a reflection, you can do a reflection, then that is one of the transformations I support, and the elements are going to be the invariants of those transformations. So if you do a reflection in a line, so you have a plane and you do a reflection in a line, then the entire plane will flip around, everything changes, except for the line that you're reflecting in. The points on those lines, they stay in the same place. Everything else changes. And so that line is actually the invariant of that transformation. Let's do 2 small examples of each, just to give everybody an idea of how wide of a subject this is. So one example of a geometry is a geometry of arrows. So that's typically the one we do where we draw all these little arrows and we do our vector mathematics. Let's call that the geometry of arrows. And the set are then the arrows, and the distance function would be the angle between them, for example. If you were to define it the other way around, then the geometry of arrows follows from the set of orthonormal transformations and their invariants. Another example would be the geometry of a family tree, right? So it's a completely, wildly different example, specifically just to show you how different it can be. So if we want that, then we have a set of elements which is basically your family tree, and the distance function is the amount of steps you have to take on that tree to get from one element in the set to another element in the set. So the distance between you and your parent would be 1, the distance between you and your sibling would be 2, and then you can define all these transformations. You could say, okay, I define the cousin relationship, and then you can work out that that's at a distance 4 and that you are your own -2nd cousin and very funky stuff like that. So geometry really is about more than drawing lines in the sand. It's really about trying to formalize these ideas of transformations, distances between any type of sets. So the last example, and that's of course the one we want, is going to be the geometry of points, lines, and planes. And that is going to follow from the set of Euclidean transformations. The Euclidean transformations are translations, rotations, and reflections, all of the transformations that preserve distances. So that's what we will want to do for computer graphics. But let's first take one step back and look at the geometry of arrows, because you've already seen that, right? And so when you have 2 arrows, 2 input arrows, which are the orange arrows, A and B, then when you look at the sum of those 2 arrows, that's going to be this one, and then the difference is, of course, that one. You all remember you have to take one vector's toe and put it at the tip of the other vector to add them together, and if you want to subtract them, you just flip one of the vectors around, do it that way. Then you have the dot product, which you should have also already learned, which gives you something that is proportional to this green guy here, and you have the cross product, also known as the erectile function, which takes two vectors and then gives you a third vector that is orthogonal to them. That only works in three-dimensional space. But the point I try to make here is that this is actually a great system. If you want to do the geometry of arrows, then this works, this is fine. And one way of telling that this is okay is, if I give you those orange arrows and nothing else, I just sort of hang them here in space, walk out of the room, I give you a paper with a formula, then you can actually reconstruct a green arrow. We will all agree that for A plus B, that's going to be that green arrow C. Yeah? Everything is there. Everything you need to know is there. This is consistent, it works, and it is something you need to know. It's not what we will be doing today, but it's something that you need to know. The naive way of going from this spot to doing geometry with points, lines, and planes, and this is something that people do. It's naive and it's not very smart, but people still do it all the time. So the naive way is to go, you know what I'm going to do? I'm going to use these arrows to point at points, right? So it was still an arrow, but I'm going to say, oh no, I'm just going to consider pointing it at a point. So let's do that, and let's see what happens when we do that. You get this. So I removed the arrows, and I left the points. Now, we actually have a problem, because if I were to fix those two orange points here in space, I walk out of the room, I give you a little piece of paper with A plus B on it, you come into the room, you cannot possibly reconstruct that green point C, because you'd need the arrows for that. You need the origin. If I say A plus B, there is simply no way that you would know which C it was. Could be any C, could be any point in the room, literally. So we've lost something here, right? We had something that we could talk about. I could give you arrows and you could construct the outcome. And now we've lost that. I give you those points, and there's absolutely nothing you can do. It could be any answer there. And so the problem here is, if you have 2 points, you really can't have all possible outcomes. There is just that much that you can do with 2 points. And this is a really, really important thing, because mathematics is a chain of binary operations. You do one calculation, then you do, it's like you do on a computer. Every calculation takes 2 inputs, it produces 1 output, right? These outputs here are not determined by the inputs, right? The points A and B, they don't contain enough information to select out point C. Could be any point C. So we could ask the question, what are the valid answers when you have 2 points? And it's actually quite easy. When you have a binary operation, a sum, a difference, a product, a geometric product, which doesn't matter which one, between 2 elements, A and B, then the answer must be on the line between A and B. That's the only place you can actually select something. For example, we could say, and we will say, when you add a point A to a point B, you will get the point halfway. And we've won something back when we do that, because now I go outside and I tell somebody, oh yeah, I left those 2 orange points hanging in the room, and here is the formula. He can come back in, and all of a sudden he can reconstruct that point. This algebra, doing this vector thing naively to geometry, is taking the responsibility of doing geometry right yourself. You can write it with linear algebra, but then you will have to write formulas that make sure that you always end up on that line, right? And that's not what I want. What I want is, I want to be able to write a random formula that is always geometrically valid. And the conclusion here now is, if you have something that deals with 2 points, the answer must be on the line. And I'm not the first one to realize that. There's actually a rather famous book in mathematics, which is called The Elements by Euclid, and it has a number of postulates in there. And the first postulate says 2 points define a line. So I want to also pose that as a first postulate, but I think we missed something. It defines a line and nothing effing else, right? It defines only the line. So when you have 2 points, what you have is a one-dimensional situation. Always, always, it doesn't matter whether you're in 17-dimensional space or 55-dimensional space, when you have 2 points, you have a one-dimensional situation. If that's the only input, the output must be on that line. So every binary operation between 2 points is a one-dimensional operation. This idea extends further. You can do the same exercise when one of the elements is a line and the other element is a point. Then you will realize that you can only select points that are orthogonal to that line, or there are 2 line outcomes. There is a very limited set of geometrically valid outcomes, and everything else is simply invalid. So that is going to be really important. This is very real and very practical for us as game developers. Imagine 2 complex 17-dimensional rigid bodies colliding, right? So they're hurling towards each other in space, and at some point they collide. Well, when they collide with 1 point from one object with another point from the other object. Unless you have large flat surfaces, that's what's going to happen in every single case. And my statement is that this 17-dimensional collision of rigid bodies is essentially a one-dimensional thing. So if I have these 2, not as high-dimensional, but still complex objects, and they are colliding, then what you would classically have to do, if you are not using the right algebra and the right mindset, what you would classically have to do is you would have to decompose these forces. They would say, oh yeah, you have to take the part of the force that is with the contact surface normal, and then the other part, and then you have the parallel part. And then, so this purple vector becomes this vector and that vector, and then this vector and this blue vector, they will collide one-dimensionally, they will just flip sign, and all of the other vectors, they remain unchanged. You add it all back together, and that gives you the outcome. But what that's really doing is you're making a one-dimensional space which sits right there where the green line sits, and you're doing the physics in that one-dimensional space. That's what you're doing conceptually. Now, my statement is, if you make sure that your operators are also always geometric, you don't have to do this decomposition, because every operation between 2 points will automatically be on that line, and between a point, it will be in the subspace of allowed possible solutions. So even if you're working in 3D, most of the problems that you deal with, most of the things that you do will either be one-dimensional or two-dimensional. Many of them will not be three-dimensional. We will be animating that spider on Friday, and most of the part will be doing it in 2 dimensions. And then even when we're doing it in 3 dimensions, all of those operations will be in certain planes. And we will heavily use the fact that it's much easier to think about 1-dimensional and 2-dimensional setups than it is about 3-dimensional setups. So this first postulate is the postulate of dimensionality. So you have to let go of the idea that the dimensionality is a property of space, right? If you have empty space, how would you measure how many dimensions there are? You can't. Dimensionality is a property of a set of elements in a space. And then you can make statements about it. But you can't do it about empty space, so you have to let go of that. And then if you add in the fact that we're always doing binary operations, then you realize that you're always working in a subspace, in a smaller space, in an easier space. And that is important. So that brings us to the main question. How do we set things up so that we always produce geometrically valid outcomes? Let's simplify a bit further, right? Our space is completely empty. We are a divine creature looking into the space from the outside, and there's only one point in there, right? A. So we're going to ask, what about the operations that we can do with just one point, right? We could add the point to itself. But we already know that there is only one possible geometrically valid outcome, and that is that the point stays in the point. There is no way to select anything out there. If you do A plus A, and A is a point, then the sum of A plus A must be a point. I've already iterated this a few times. It must be a point, and the only position it can be at is at A itself. So that is geometry's way of telling us that it is homogeneous. And homogeneous means, like, if you do x equals 2, that's the same as doing 2x equals 4, that's the same as doing 3x equals, and so on. So it is homogeneous. And what you get when you add A plus A, you get another point at the position of A, but it is twice as energetic, or twice as heavy, or twice as happy. I always have happy points. So 2A is twice as happy as A. Now, when we only have one element, one point in our space, we're pretty much quickly done talking about the elements, of course. But remember, when we do geometry, we didn't just want the elements, we also wanted the transformations. And that's also very easy in this case, right? If you have an empty space and there's one point in there, then you can't move it, you can't rotate it, everything looks like the identity transformation. The only way that you can determine that something has moved is if you compare it to another position or another point, but you only have one point, so you can't do that. So the sums and the differences, they will often relate to elements. The geometric product is going to relate to transformations. And in this case, since everything looks like the identity, we have a very simple scenario, and which is, of course, where our geometric numbers come in again. That is that if you multiply A with itself, you just get the identity transformation, which says this is an element that is not a real number because it was a point, and it squares to +1, right? So that's very directly that. Okay. Now, of course, the space with just one point is a little bit boring. So we add in another point, right? And what about A plus B? Well, there's really only one sensible geometric choice. If we assume that at the beginning A and B are equally happy, then A plus B will be at the average position, and it will be as happy as A and B are together, obviously. Always happier than alone. And then we can also ask the question, what about the product AB? So we remember when we did the product, we were going to get transformations, and what the product AB will give us is a translation from B to A. It'll actually be twice the distance, but that's a technical detail. So it'll give you that translation. Is that the only transformation that we have in this space? Well, no. We can do more than translations in a one-dimensional space. We can't do rotations, obviously, but we can do reflections. So what we can do is we can reflect the point B in the point A. So we consider A to be a mirror, and we reflect the point B in the point A. And that will turn out to be done by the formula ABA. And then, of course, if you turn it around, you get the formula BAB, the other point reflected. All of these operations are completely well-defined. These are the type that I can write on a piece of paper, go outside, you come back in, you execute this, you will find the same result I do. But they work with points, not with arrows, right? And so we really couldn't do that with the standard vector and matrix approach. To make sure that we understand how we will do this in code and when you have to calculate this, let's quickly run over this and how you would implement this, how you would approach this. So let's assume first that our point A is at some position, let's call it 1. So we'll just say it's defined by the equation x equals 1, right? And then we will make it explicitly homogeneous. So if we want to make it explicitly homogeneous, we can sort of do that by getting 0 on the right-hand side, right? It tells you, you can multiply this with anything. And it'll stay the same, because 0 multiplied with anything stays the same. Yeah? So we do that. We do x minus 1 equals 0. Then the B point is just at x equals 2. So in the same spirit, that becomes x minus 2 equals 0. And this actually sets us up to use our special elements to write this down. So now we can write it down as elements of our algebra. And x minus 1 equals 0 is going to be x E1 is x, minus 1 times E0. Because it could have been in this view when we wouldn't have known that it was a line even. We just calculate it, get the other thing. And that's what actually will also be the case. So everything that we've done so far automatically extends from points to parallel lines. And not just parallel lines, because if we add a dimension more, yes, then it turns out that those things you thought were lines aren't lines at all, they're planes, right? And so we learn that the product of two parallel planes is a translation. Why? Well, because when you have two parallel planes, you can always move your view so that they look like lines, parallel lines, and then you can always move your view so that they look like points. So you can make them look like a duck, you can make them quack. So that's a translation. It's always a translation. There is absolutely no choice here, right? So what we learned is lines must be line reflections, but we only looked at parallel lines, right? So the only thing, oh, that's one too far. The only thing we did so far is this. We took a line reflection in one line, and then we added a line reflection in another line. And as you can see, that produces a translation. It's also a translation with twice the distance between the lines, right? So if we change the distance between the lines a little bit, then the translation will change it twice as much. We can now just look at what happens when our lines aren't parallel, because we know lines are line reflections. So we do one reflection, and then we do another reflection in an intersecting line, and what we get is a rotation, right? And it's again a rotation with twice the angle between the original mirrors. So you have your two mirrors, and they intersect, you get a rotation. When they are parallel, you get a translation. Now there is one last case that is also very important, and that is a point reflection, right? So if we do two reflections in orthogonal mirrors, then what we get is a point reflection. And that's important because we already know that point reflections were fundamentally associated with points. And this tells us that in 2 dimensions, you can represent a point reflection using orthogonal vectors. And now we think back to the algebra part, where we multiply two vectors and we got a scalar part and we got a bivector part. The scalar part was the dot product, and for orthogonal vectors, the dot product is 0, right? So if you have orthogonal vectors, you would only get a bivector part. So the elements that represent points in this two-dimensional setup, they will be pure bivectors. They will always be this combination of orthogonal reflections, because that's what gives you a point reflection. Building up elements by combining other elements is absolutely key here, right? So that's a very important thing. And then there is a last thing that I want you to really realize, and I'm going to leave this running for like a few seconds. This is the idea of the gauge degree of freedom. So in all three of these cases, it doesn't really matter what the exact mirrors were. The only thing that matters here is how they are oriented and what the distance between them is. So I'm changing these mirrors, I can move them both at the same time, and I still get the same transformation, right? I still get the blue triangle translated to the red triangle. Even though the in-between result is different, the final result is always the same. And so any of those mirrors here, I could pick these two mirrors or when they are somewhere else, they will all produce the same translation and you get this gauge degree of freedom. And the same thing happens with the rotation. If you rotate both mirrors at the same time, then you will always end up getting the same rotation from the blue element to the red element. And similarly here, which orthogonal mirrors you use doesn't matter. They just have to intersect at this point, and then you will always get a point reflection in that point. These gauge degrees of freedom are key, absolute key if you are doing practical geometrical problems. And we'll do a very small one in a few minutes to really drive that home. So that's very important. Good. We are going back to our divine creature view. And we are actually going to look at the algebra really quickly again, because what we saw of this equivalence principle is very, very apparent if you look at the algebra. So if we started in our one-dimensional space, we said, oh yeah, the point A, for example, has the position x equals -1. So if we make it homogeneous, it becomes x plus 1 equals 0. And if we write it down in geometric algebra speak, we will write E1 plus E0. Right? Well, in the one-dimensional space, x equals -1, it picks out a single point. You have one dimension, you put some coordinates on there, and you say, okay, the point at -1, right? But in a two-dimensional space, x equals -1 is a line. There are a whole bunch of points for which x equals -1. All these points have x equals -1. They all fit the equation. And if you go to a three-dimensional space, it becomes a plane. The same equation and the same multivector can just have all these different meanings. And that is sort of to be expected, right? Because I already told you that if you can make it look like something, then it actually behaves like that. And that should make sense now because the algebra is exactly the same. Yes, I am changing how it looks, but I'm not changing the algebra. It is always E1 plus E0. And surely, if I take two of these guys and I multiply them, if it generates a translation once, it'll generate a translation always. So this thing of moving the view is really fundamental, and it's very true, right? Because the algebra didn't change. We just changed the way we looked at it as divine creature, right? Good. So what we have here is we have the same meaning. It's always x equals -1. It's the same algebra. It's always E1 plus E0. But the geometry changes depending on what space you're looking at. And that's really just a perspective type of thing. As a divine creature, you can always find that space where it looks easier and do it there. And so they must always be equivalent, very important. So what about the point then? If you don't, if it wasn't a line, it's a point. And I already told you it's going to be a bivector. But this is actually also very easy to see how that works. It's still going to be the same point reflection, and it's still the same point there as it was in this case. And to see why that is, let us look at this particular bivector. So this is E12 plus E02, and you can write it as the product of E1 plus E0, which is this guy, it's that line, right? And the product of E2. But E2 is, of course, also a line. It's that line. It's the y equals 0 line. And now we see exactly what's going on, because these are two orthogonal lines, which we know produces a pure bivector. And we also saw that the geometry of two orthogonal lines is a point reflection. So it is a very natural way to represent, if you're in this two-dimensional space, to represent your point using this bivector, using this idea of representing it as two reflections. And of course, as you could have guessed, yes, this completely generalizes to higher dimensions. Everything stays the same, and you can totally run with that. So, product of two orthogonal vectors is always a pure bivector. Reflecting in two orthogonal mirrors is always a point reflection, and their intersection is, yeah, well, always two lines intersect in a point in the plane. All right. So what I want to talk about now is we want to get that bag of operators, right? That bag of things that we can do. Now that we understand a little bit how this is sort of a structure that is very intricately connected, let's think about the operators. And of course, we remember that if we added the two green points, we got the orange point. Because of our law of making ducks quack, that means, of course, that parallel lines are also, if you take the sum of two lines and they are parallel, you get the line in between. That's because this needs to work, right? So that's already solved. So what about intersecting lines? What happens when you add intersecting lines? Well, when you add intersecting lines, you also get the line in between. We call that the bisector. But of course, when we add intersecting lines, we realize that there are two bisectors. We have this orange line, which is indeed halfway between the green lines. But this other orange line is also halfway between the green lines. And so that's a bit funny, right? I mean, when they intersect, we have two bisectors, and when they are parallel, we don't. But we do, actually. Because if we look at the 3D version, and I can turn it a little bit, what happens with that second bivector, as these green planes become orthogonal, that second bivector shoots off to infinity, right? That's actually the bisector, not bivector, bisector at infinity. And this also tells us exactly what was happening with our parallel setup. When you have a parallel setup, you also have two bisectors. You have the line halfway between, and you have another line which is also halfway in between them, but it is at infinity, right? And that is going to be represented by the difference. And now we could actually, because I skipped the difference when I was talking about points, but now we realize because when you add 2 points, you get a point halfway, which was on the line, it's a valid answer. When you subtract 2 points, you get a point on that line at infinity, which is also a valid answer, geometrically valid, because it is on the line defined by these 2 points. So when you subtract it, you get a point at infinity. And now you guys should be thinking, hey, I know this from somewhere, because of course in computer graphics, when we have homogeneous points, we do w equals 1. And when you subtract 2 points, you get the vector that points from one point to the other. That's that same thing. That's that exact same idea that we have here, but applied to geometry. And when you apply it to geometry, it gives you that point at infinity. Good. So this is the entire amount of complexity that exists. And we can actually see why. When we had 1 point, we only had the identity operation, right? Then when we went to 2 points, we got point reflections and translations. When we go to lines, we get translations and rotations. So we get something new. First we get translations new, then we get rotations new. Now when we go to planes, we get nothing new anymore, right? And that's very fundamental. When you have planes, you still just have rotations and translations. And again, you can use this God view mode to understand why. When you have 2 planes, they're either parallel, and we already know when they're parallel, you just turn them until they stick through your eye. They look like lines, and you've simplified them. When 2 lines, so it can't be any more complex than lines. When they're not parallel, 2 planes always intersect. When planes intersect, they intersect in a line. You stick that line through your eye, and it again looks like 2 lines. So even though we added a dimension, we still get nothing new. It stops at lines. You get translations and rotations, and that's it. When you combine lines, you get it. When you combine planes, you get that. When you combine volumes, you get that, and it keeps going on, and there's never anything new. So that's quite fascinating. I mean, that's where the complexity stops. And this is all you need to know and understand, and it'll turn out to be very fundamental when we want to do practical things with it. So I have a little overview here that tries to show that points and parallel lines and parallel planes, they're all the same thing. When you add them, you get that bisector in between. When you subtract them, you get that bisector at infinity. When you multiply them, you get a translation. Then you have intersecting lines, intersecting planes, intersecting volumes, and so on. When you add them, you get the first bisector. When you subtract them, you get the second bisector. And when you multiply them, you will get a rotation. Or in other algebras, you might get a boost and other physical type of stuff that you might want to have. But for us, it's be easy. Translations and rotations is all we do. So at this point, we are actually starting to get at a place where we can say we have an algebra of geometry. We took a set of elements, and there weren't even any numbers in there at this point, right? I just put the points in there, and I put all the lines in there, and I put all the planes in there. And then I define operators between these elements. What happens when I add points? What happens when you make them more happy by multiplying them with the scalar? What happens when you compose them, when you use a geometric product on them? So we did everything that you have to do to define an algebra, but we have no numbers in the bag. We have actual geometry in the bag. And that is a big deal. But we're not done yet. To get a good understanding and to do this practically, we will need to look at these geometric gauges again. We're almost done, but not done yet. So the general procedure is you always want to pick the viewpoint where things are easier, right? If you can find one of these viewpoints where you can make it look like points, do that first, and then it'll be much easier for you to think about it. But then, at some point, you can't make it look any easier than it is. And then at that point, you can use the geometric gauges to understand what's going on. So let's very quickly review those geometric gauges. So we know that 2 intersecting reflections, 2 intersecting mirrors creates a rotation, 2 parallel mirrors creates a translation. This blue one is just a single mirror. There's no gauge degrees of freedom on that one, right? If you move a single mirror, you get a different reflection. You don't have any freedom there. But then, of course, if you reflect in a point, you do, again, have some freedom on which mirrors you pick to create that point reflection. And this is the exact gauge degree of freedom you have. So you can rotate the green one around its intersection point. You can move the purple one without rotating the lines or changing the distance, and that will always give you the same transformation, the same translation, the same reflection, and so on. Good. Now, this allows us to understand what happens with all of the different products in geometric algebra. And I'm going to give you a first example. So the first example is a geometric product. So imagine we have 2 points in the plane, and points are point reflections, and point reflections are reflections in 2 orthogonal lines. So the red thing is a point, visualized by these 2 orthogonal lines, and so is the blue one. What can we now do? So these are all reflections in mirrors, right? Every line you see is a mirror. I will now use the geometric gauges of this first one to have one of the mirrors go through the blue point. And then you use the geometric gauge of the blue one to have it go through the red point. But now something happens, right? Because you take 2 mirrors and you make them the same. And when you make them the same, you're doing a reflection, then you're doing the same reflection. It's like doing nothing, right? So it falls out of the expression. So if we take the geometric product between 2 points, that's what it'll do. The geometric product will, for you don't have to, I did it manually here. The geometric product does this automatically for you. It'll rotate these mirrors around, and it'll try to find things it can simplify. Can I make some of these mirrors the same? And so what we end up with is just this red and this blue one, and we see that these are 2 parallel mirrors. And we know that parallel mirrors generate a translation, which is exactly what we expect, because we took the geometric product of 2 points, and I already told you 4 times, when you take the geometric product of 2 points, you get a translation, right? And you've seen it happen now. This is how the geometric product does that. And you should also notice something. We started with 2 red and 2 blue, and we end with 1 red and 1 blue. That means that in order to understand all of this, you must look at rotations as being 2 reflections, because it is 1 reflection from this side and 1 reflection from the other side that cancels. And that is very fundamental. We're going to actually do the same exercise for rotations in a minute again. It's very important to realize that. So when people use quaternions and they use I, J, and K as name, then you should go, because that's exactly what stops you from understanding quaternions. They should be called something with 2 names, because there's 2 reflections, and when you combine rotations, it's one of each that drops out. Always 1 of each. Good. We did a geometric product, and we say the geometric product eliminates identical mirrors. So it does the gauging, finds mirrors that are identical. The dot product does something similar. It eliminates not only the identical mirrors, but also the parallel mirrors. So here I have a dot product between a point and a line, and let's see if we can find any parallel mirrors. Yes, we can. When we find parallel mirrors, they will get eliminated. That's again something the dot product does automatically for you, but this is how you can understand it. So if you take the dot product between a point and a line, you get a new line, and that new line will be orthogonal to your original line, and it will be through your original point. So this red line is orthogonal to the original blue line and through the point, right? And you can do this in 3 dimensions, and your point would be 3 planes, and you can rotate it a bit more, but you can still use the same rule. You just try to find parallel reflections, you imagine they go away, and whatever is left over is going to be the answer. Another product that's very important is that joint product. So what does the joint product do? It finds identical mirrors, and instead of throwing them away, it keeps them, right? So if we take, again, the joint product between these 2 points, we will get the exact same procedure, but now the identical mirrors stay. And when you do this with 2 points, you will find the line that connects the 2 points. The blue-red line here is the line that connects our original 2 points. And how did we calculate it? With a simple product. And what did the product do? It just found the identical mirrors. And in the previous exercise, we found an orthogonal element through it with just a single product. So this would normally be half a page of code, right? To figure out the coordinates and do the vectors and then make your representation of the line. And it just becomes a single product here. The outer product can actually take any random mirror, and it will find an orthogonal representation through this point. So remember the outer product, when we took two vectors, we got a scalar part and a bivector part. The bivector part is E12, that's always orthogonal. So if you take the wedge, you will get just this orthogonal answer, and it looks a little bit like this. If you want to imagine what it does, it basically opens this thing up until it's orthogonal and says, yes, you will get the pure point. You will get that pure orthogonal part of this composition. So these four ways of thinking about these reflections are all you need to actually understand most of the expressions that we need in computer graphics. Things are bouncing around and we want to calculate reflections and intersections and so on. And you can think about all of that using nothing but just these tools. I'm going to give you an example. So I told you about the projection formula, b dot a times b, or in this case, b dot a times a. And this will actually project, we have a point and a line here, it will either project the point on the line or it will project the line on the point. So they both start the same way, they both start with b dot a. We remember the dot product eliminates parallel reflections. So good, we use our geometry gauge to create parallel reflections. So those two white guys are dead now, and all we have left is this red line. That red line is b dot a. Okay. If we multiply b dot a with b again, then what we get is an orthogonal, a product of two orthogonal vectors exactly at this point. And that is, of course, the projection of our original point A onto the line B. If we do the other one and we multiply with A again, so A already was this orthogonal set, we multiply this guy with this guy and this guy, then the geometric product eliminates identical mirrors. And so there's actually two mirrors here, the one from A and the one from B dot A. So if we do this, we will get the green line. And the green line is exactly the blue line projected onto the point. So this formula, and it will actually work for anything, you can really project anything onto anything. You can project a line on a plane on a line on a point, and you can figure out how it works by just using these gauges, and you'll go, oh yeah, I can see how that works. So that's something. You need to practice it a little bit, but this is the visual model that replaces what you normally do by drawing arrows everywhere. You can now say, no, I'm going to think of, I see a 3 vector, okay, I'm going to think of it as 3 reflections, I can rotate it like this and like this, and this will cancel out and that will happen and so on. So that's how we do that. Then this is another fun example. So what we have here are 2 rotations, right? So we have 2 reflections here and 2 blue reflections. And again, what can we do? We can rotate one of them to go through the intersection point of the other. And then we can do it like this. And then those 2 reflections, they drop out. Because when you do the same reflection twice, you could have just as well done nothing. If you actually do it and you're not lazy enough, so you have to avoid that. So this is actually how you understand how rotations compose. If I do 2 rotations and I compose them, then I will get a new rotation, right? And it'll have a new angle, and it'll have a new center point. But where is that center point, and what angle is that? And this is how you understand that, by looking at them as reflections, because then you can gauge them to find these identical mirrors. And again, we are left over with 1 red guy and 1 blue guy. This is half of one rotation and half of the other rotation that remains, and the inner part collapses away. And this tells us exactly, okay, now we have a rotation around this point with twice the angle here, and when we started, you wouldn't have been able to guess, right? I mean, if I tell you you have that rotation here and that rotation there, and I'm going to do both of them, what is the final rotation going to be? Well, good luck. If you're not thinking about it as reflections, then there is no real way to intuitively approach this. But if we do it with reflections, we can easily say, okay, I can gauge these because that doesn't change the result. And so I can make these identical mirrors, they drop out, and now I can see exactly what my combined rotation is. Let's see how late it is. Ooh, I'm running late. I want to maybe skip to an example. So this is actually, this is a nice slide that I'm going to skip some slide, guys, because I don't want to get into everybody else's time. So this is an extremely nice slide. This shows the entire structure of everything I've been talking about, right? So when you look down here, for example, you see 2 points, makes a translation, that's the same as 2 parallel lines, that's the same as 2 parallel planes. Similarly, from intersecting lines, you can make a rotation, which is the same. This isn't orthographic, so I can't turn it exactly where you can see that it's the same, but it's the same as those intersecting planes. In 2 dimensions, you can also do a transflection. It looks like that in 3 dimensions, and then you just keep getting more and more combinations of the same thing. But this is it, by the way. It stops at 4. You can't do anything more than 4. I had a demonstration of that, but I now skip that slide. And then the orthogonal ones, they are special, right? They are the points and point reflections. And in 2 dimensions, we use 2 orthogonal lines to represent a point reflection and a point. And in 3D, we use 3 orthogonal planes to represent a point reflection and a point. And similarly for the lines and the planes. So these we call blades. Because they are the products of orthogonal elements. So they don't have mixed grades. They are all pure grade. This thing is going to be grade 1 in each of its own respective algebras. This thing is going to be grade 2 because you have 2 reflections. This thing is going to be grade 3 because you have 3 reflections, and so on. Okay. So just 2 minutes. I just want to show you how it now actually works, because otherwise all of this has been for nothing. So please bear with me. So what I have here is actually something that is very relevant to computer graphics. As soon as you move away from the pinhole camera model, you will want to implement a lens system because you want to have fancy depth of field. When you do a lens system, this is the equation that you will find on Wikipedia. It tells you, okay, if I have a certain point somewhere and then I have a lens with a certain focal distance, where is my image point going to be in focus? Right, and if I were to have my screen somewhere here, then I would know that this point would be blurry. It would be this blurry at this point in the scene. So this is called the thin lens equation. It's actually called the paraxial approximation for the thin lens equation, but let's not get into the details. The thing is, how do we classically do it? Well, normally you would do something like this. You would have some random origin, and you would use an arrow to point at the center of the lens, right? You do the things that pointy thing that you really shouldn't do. And then you have another arrow to point at your image point, and then you have another arrow probably to point at your focal point, and then you probably want to subtract that last arrow from that first arrow to get that little green arrow there, and that little green arrow is actually, of course, not really there. It's there at the origin where all the arrows live. And then, yeah, you have that other arrow, and then you subtract and blah, and then have to move that there too. And then you gotta normalize some elements and take some dot products to eventually find the distances that are the input here, because they want you to find this distance d and this height h before you can even start using this formula, right? And then you get this formula, and honestly, this formula, it means nothing to anybody, right? Sure, it produces whatever it produces, and then that's it. That's how you typically look at that. And it's not pretty, it's complex. So what does it end up looking like in geometric algebra then? How is it different? And also, what I want you to really realize is, geometric algebra is not taking your current formulas and going, oh, there's a cross product here, let me change that by a wedge product, and now it's suddenly going to be magically much better. That's not it. You really have to think about the problem from the start again, but where you end up is so much nicer. And so this is where we end up. And of course, it's also, you need to still learn how to read it, but it is actually quite easy to read. So let's read it together, and because everything is new from this morning for you guys, here's a little cheat sheet. The V is the join operator, that's how we typically write it. The wedge symbol is the meet operator, and the dot is it's the dot. So the formula starts with P join F. So P is this point that we want to calculate the image of, and F is this point that sits at the focal point of our lens. So if we say P join F, we actually get this line through P and F, right? We do the thing where we find the identical mirrors and we keep the identical mirrors. That's this going on. So we end up with that line. That's just this expression, all right? That's how we start. What do we do then? Then we say, oh, intersect that with L, and L is this lens line. So if we intersect the line through P and F with L, we find this point here, right? Okay, next step, we take the dot product with L. So remember, dot product eliminated parallel mirrors. We just created a point which are two orthogonal mirrors, so there's a line here and a line here after we do the intersection. And by taking the dot product, we actually take this line L out of there. And so we end up with this straight line, all right? And then we intersect that with the join of P and C, which is this line. So we basically intersect these two lines to find the point E. So yes, you have to learn how to read this, but you can read it from left to right. You can say, oh, I joined this point with this point, then I intersect it with the L line, then I take the orthogonal ray out from the L line, and then I intersect that with the join of two other points. Completely readable expression that, yes, you have to learn how to read it, but it's right there. The geometry is right there. There are no measurements here, right? There is no, you have to measure the distance from the lens to the point, and then you have to measure the height, and you have to be in a preferred coordinate system where the origin is at the center of the lens, and the x-axis is aligned with the axis of your... That's what you have to do in the classic approach, by the way. But we don't have to do any of that. We just do the geometry. We just go, oh, you know what, how does that work, a lens? Well, the rays that go through the focal point, they exit the lens at a right angle. And the rays that go through the center point of the lens, they just go straight through. Well, that's this written down directly in geometry. And it gets even better because we don't have any coefficients here, right? What we were calculating earlier, the D and the H, were actual coefficient things. You would go out and measure these distances, and you get another number out, and you measure, and then you go, oh yeah, that's the imaging point. We don't have any of that here. And that gives us an important advantage, because what if we use the same formula, but instead of imaging a point, P, I keep the formula, and the only thing I do is I change P in Q, which is a line. Well, it still works, right? Because when you join this line with this focal point, we used to get a line, now we'll get a plane. So we'll get this plane going through. And then the other one is also a plane. And in the end, you get two planes that intersect, and they produce the line J, which is the image of the original input line through the lens. But it gets even better. What if we keep P a point, but we change the focal point and the center point of our lens into a line? Well, then we get a cylindrical thin lens, right? So you have these cylindrical lenses that are not, they're cylindrical. and what they do is, when you image a point, you get the point as input and you get a line as output. And it's actually quite funny, because when I first made this formula and I noticed this, I wasn't really sure whether or not that was physically correct. So I actually had to call some prof in optics and go like, oh, if I image a point in a cylindrical lens, oh yeah, that produces a line. Oh, phew, okay. So it made me really happy. So this is a bit of a practical example of what it looks like when we do geometry with geometric algebra. Simple expressions that you can all directly read, that you can reason about, oh yeah, I'm joining these points and I'm intersecting it like that. Just that thinking process is already the solution. Yeah? Normally you do the thinking process, then you Google how you have to calculate the intersection of a blah and a blah, and you work that out. None of that is needed, right? You just do the thinking part and you're done, because the thinking part you can write down directly. Okay, so we got there. Thank you for bearing with me. All right, so I think we'll push back the next session a little bit and start yours at 1. That gives 40 minutes to eat. So Amish is talking next. He did a presentation at the Game Developer Conference about this algebra, and he is extremely good with real-world examples. So if I was a bit too abstract for you, or you're overwhelmed and you want to take it a tiny bit slower, you want to see some of these mirror stuff in action, then check that talk. People paid good money flying to the GDC to hear the very same talk. You guys are getting it for free, so don't miss out. Okay, so that's in 40 minutes. Thank you.
Smoothing out the world from the coast of California. Smoothjazz.com, global radio.
Coming in on a trade wind.
I'm thinking about a future feeling.
This is the captivatingly fresh voice of Hawaii's Malin Abran on her new album, Time Is Now.
So don't let nobody bring you down. And don't let no sad days stay around.
Soulful jazz and positive pop, this sophisticated blend of vocals, piano, and muted trumpet features world-class production and Grammy-winning musicians.
I'm looking for something.
Delivering the spirit of aloha to the world, Time Is Now is available in the smoothjazz.com listening loft and everywhere you source exceptional music. Discover the artist at malinmusic.com.
Looking for something till you walked by.
Join jazz enthusiasts from far and wide for the 13th annual Lake Arbor Jazz Festival in gorgeous Prince George's County, Maryland, June 12th through the 16th. 5 days of smooth jazz and classic R&B with performances by multi-platinum and Grammy-nominated saxophonist Najee. Jazz fusion group Pieces of a Dream, acclaimed jazz sax man Mike Phillips, singer-songwriter Eric Robertson, chart-topping flutist Kim Scott, legendary soul-funk band War, and many more. Tickets and information for the 13th annual Lake Arbor Jazz Festival available now at lakearborjazz.com.
Meet touring and recording guitarist Steven Duros. While a challenge to categorize musically, his flamenco-drenched smooth jazz features reggae, pop, and Arabic rhythms. You're listening to highlights from his anticipated fourth album release, The Manhattan Sessions. Find this musical gem in the smoothjazz.com listening loft and meet the Manhattan Sessions composer at stevenduros.com.
smoothjazz.com. The world is listening.
Hey, yeah. The world is listening
To smoothjazz.com.
older now, my superstitious. Looking back on that girl who was so ambitious. I've had all the lessons in love, but I'm grateful for the ones who broke me, grateful for the ones who woke me, the ones who led me here to you. And I wouldn't change a thing. No, I wouldn't change a thing. Now that it's you, my search has ended. I didn't know I could feel so contented. My love is all I have to prove to you. I've agonized over life choices, fought with all my inner voices, and now one voice calls out to you. And I wouldn't change a thing. No, I wouldn't change a thing. And you can wait a whole lifetime for a lifetime of happiness. And one moment shared we'll never forget. Like the day we met makes up for all the lost time. And I wouldn't change a thing. No, I wouldn't change a thing. Wouldn't change a thing. Wouldn't change a thing. Wouldn't change a thing.
Montserrat. SmoothJazz.com Global. Smooth Global Living.
From her forthcoming album, Ski Harvey pre-releases the title track, produced by renowned South Korean singer-songwriter Kelly. This is Waiting.
You keep me waiting, baby, it's you. Keep me waiting, baby, it's you.
So much life happens in the in-between. Let's be sure to live it all while we're waiting.
No matter how long it takes, speak those words again. I can hear this voice spinning in my head.
What are you waiting for? Find this powerful new piece in the smoothjazz.com listening loft and on all of your favorite music platforms. Meet the artist at skiharvey.com.
This is the 10th album release from guitarist Will Sumner, Meadowlark, on Guitar One Records. Handcrafted contemporary jazz with stirring and reflective compositions, inspired by a beautiful farm owned by the artist's grandmother in Apple Valley, California. These magical memories can be yours now. Meadowlark is available in the smoothjazz.com listing loft. Discover more at willsumner.com.
The physician musician, Dr. Clarence Taylor, returns with a memorable, intimate collection of jazz, R&B, hip-hop, and more on Welcome to Doc City, Deluxe Edition. From melodic ballads to soulful grooves with relevant lyrics.
My heart just won't give up.
This long-awaited recording is a collaboration with extraordinary musicians, including 4 Grammy winners.
Your cousin said he said you really love Sade, so I got the greatest hits before I arrested your body.
Welcome to Doc City. Deluxe Edition is available now in the smoothjazz.com listening loft and everywhere you stream your tunes. The Doctor is in at DocCityMusic.com.
Wherever you go, we'll be there.
Ready, right? Okay. All right. So, welcome back. Good to see that there are still quite a few people here. That's nice. So the next speaker is Hamish Todd. He works for Imagination Technologies, which is a GPU building company. And he gave a talk at the end of March at the Game Developers Conference about PGA. Actually gave 2 talks. And today you are getting a condensed rundown of both of them. They include many practical examples about what we've been talking about so far. So, Hamish, all yours.
Thank you very much, Stephen. Okay. Yep, we've got there. And I've got a little prop here. This one will do. So it's a little cow. All right. And I, J, and K, they are all 180-degree rotations. So you can have so let's say that this one is I, 180 degrees around the y-axis, and then J is 180 degrees around the x-axis. But it said something about squaring them there, and what that means is something like this. 1 second. So we're going to do I squared. I'm going to introduce some labels that's going to make this very, very obvious sounding, but we're going to say that this is 1, and then this, with my arm kinked up, is -1. The cow is in the same place with 1 and -1, but my arm is kinked up. All right, so we do 1, and then we multiply by I, and then we multiply by I again, and look, we've got -1. Ooh. And we can, in fact, multiply by I again, and that's -I, and we multiply by I again, and that gets us back to 1. Do the same thing with the x-axis. Start with 1, multiply by j, multiply by j again, so that's j squared. And look, it's -1, my arm is kinked up. Multiply by j again, and multiply by j again. And k is the hardest one, all right? Okay. 1, multiply by k, multiply by k, multiply by k. It's not, I didn't cheat, promise. Multiply by k. Thank you. I think I deserve some round of applause for that. Yes. Okay. Incidentally, oh yeah, I got to do this part because we're in Cortec, and good to know how to pronounce I, J, and K finally. It's apparently ek. So here we go. Right. I, J, K. -1. Right. So that's how this connects up with geometry, all right? Whenever you see an equation like this, you should say, what's the geometry? All right. Yes, and as Stephen said, I'm not a professional gymnast. I'm a graphics researcher at Imagination Technologies. We make GPUs. If any of you have got an iPhone in your pocket, there's a good chance that we made the GPU in that. Before that, I was doing a PhD on virtual reality for structural biology, where I used quaternions a lot. I also spent some time in the games industry, made a Hello Kitty branded game that never came out. Before that, I was a maths teacher, actually. And I can tell you one thing as a maths teacher. Quaternions are 4-dimensional is a damaging and useless thing to say because quaternions can be visualized completely in 3D. I am a huge fan of 3 blue 1 brown and number file. I love all their other videos, but they gave an explanation of quaternions based on them being 4-dimensional. I can't say that they were good explanations. Yeah, all right. So in this talk, we're going to climb, you're all on a journey. You want to be able to get to the top of the mountain, which is being able to write a good game math library from scratch. But there's loads of things along the way. The way I'm going to take you through it is that first we're going to think about quaternions specifically, and we're going to think about quaternions as a mixture of some amount of 180-degree rotation and some amount of 0-degree rotation. If you don't know what that means, don't worry, we're going to go through it. All right, dual quaternions is a generalization of quaternions that allow you to move away from the origin. Don't want to be bound up with the origin all the time. In section 3, we're going to think about points and other things that you can make with reflections. Stephen has already talked about this, but I'm going to ground us in video gamey stuff. but I'm going to ground it in video gamey stuff at the end mostly. So I'm going to think about measuring angles, distances, intersections, and projections, which lets us solve lots of problems in video game programming, right? If you're programming Lara Croft, then you've got to make it so that she can reach out and grab a branch. If you're programming a game about going around on a spaceship, you've got to make it so that the player can control it properly. If you're programming a game about being shot at by a sniper and trying to defend yourself with this and that, basically you need, in all of these cases, points and lines and planes. You need to know really, really well how to solve problems involving points, lines, and planes. I haven't done it for the lightsaber thing because the lines are a bit obvious in this picture. All right, so part 1A. A quaternion is a mixture of some amount of line, which rotates by 180 degrees, and some amount of identity, which rotates by 0 degrees. And the fancy way of saying this is that a rotor is a linear combination of a bivector and a scalar with coefficients in the reals. I don't like talking that way. Okay, quaternions that rotate by 180 degrees specifically. So I'm going to come back in here and do that. Right, so here we've got a quaternion, and this is the way that you'd see a quaternion in Unity or Unreal or something like that. So no I, J, K, instead we call them X, Y, Z. They're just the same thing. This quaternion has everything set to 0 except for the Y, which is equal to 1. And that is a rotation around the Y-axis, all right? If you've got a 3D model of a cow and you apply this quaternion to it in your game engine, you'll be turning it around that way, of course. And you can visualize this quaternion this way. There's a visualization I really like. So you've got a line, which is the y-axis. You've got an arrow saying I'm going 180 degrees around it. Here is another quaternion. X is 0, Y is 0, Z is 1, W is 0. This one is a 180 degree rotation around the Z-axis. Oh. Better keep this the right way around, so it's a rotation like that, because that is the Z-axis, at least in the coordinates I'm used to. Again, we can visualize it this way. You've got an axis, you've got an arrow going around it saying you're rotating 180 degrees, and no prizes for guessing what this one does. It rotates your 3D model by a 180 degree turn around the X-axis, right? And you can visualize it as the X-axis with that arrow again. And you might look at all of these. Beg pardon? No, don't worry. Yes, there's nothing that you're supposed to see over here. Yes, I'm used to this. All right, X, Y. You might look at these X, Y, and Z, and say, all right. Well, leaving out W for a second, these sound a lot like vectors. All right, these sound a heck of a lot like vectors. They've got an X component, a Y component, and a Z component. And indeed, if you imagine the vector that has the components here, well, that vector would be pointing along the axis that we've been talking about here. So you might say, well, come on, you're bringing in this new visualization. Why don't you just use a vector? Come on. But I put to you that there's something distracting about a vector, certainly in this context, because in this context, you really don't care about how long the vector is, all right? The way of getting from this vector to one of these is that you put an arrow around it this way, so we're using the right-hand rule here. You put an arrow around it that way, you extrude the shaft of the vector, and then you get rid of the head, so you can no longer see how long the vector was. You do know which direction the vector was pointing. You know whether the vector was going that way or that way, because the right-hand rule has made it so that we've gone this way around it instead of the other way. So you do care about whether the vector was this way or that way, but you don't care about the length of the vector. You really don't. Okay. Quaternion multiplication is rotation composition. Stephen has made this fairly clear, but for a video gaming audience, so rotation composition means I've got a vector, I've got a rotation such as this one. And let's say I want to follow it up with another rotation, right? So in this case, I'm doing a rotation around the y-axis, followed by a rotation around the z-axis. And that gets me to there. And suppose that I wanted to skip straight from here to here. I wanted to do this rotation. And it turns out that there is a rotation that does that. There is always a rotation that does that. If you do two rotations, there's always some rotation that takes you all the way from there to there, certainly if you're talking about 3 dimensions. And it turns out that that is precisely quaternion multiplication. So you take the quaternion representing this one, take the quaternion representing this one, and you do this thing that we call quaternion multiplication. It's available to you in Unity and in Unreal and whatever. And it gives you, in this case, rotation around y-axis followed by rotation around x-axis gives you a rotation around the z-axis. All right. Quaternion addition, which is rotation averaging. All right. What do I mean by averaging? Well, here's an analogy that I really like. So if you're thinking about colors, then any 7-year-old can tell you that if you mix together blue and red, you get purple. All right. Similarly, you can mix together quaternions. So here I've got two quaternions, and I'm going to try to mix them together in some sense, right? So I've got the y-axis quaternion. I have already told you this one. It's the 180 around the y-axis, 180 around the z-axis. What do I get if I did like x plus x, and then y plus y, and z plus z, and w plus w? Oh, here's what it does to the cows, by the way. Well, clearly I'd get this one. It's got a y component is equal to 1, and a z component is equal to 1. And it turns out that this quaternion is a 180-degree turn again, and it's a 180-degree turn around the axis that's directly in between the y-axis and the z-axis. So there's one of the quaternions that we're mixing, there's the other one, and then their mixture is a rotation like this, right? It's going around this axis. All right. That's what it does to the cow. You might have hoped that we were sick of 180-degree turns at this point, but no, we've still got more to hear about 180-degree rotation quaternions. But there's something that I've been sweeping under the carpet for a moment here, which is that if you add together blue and red, if they got equal amounts, you don't exactly get this. You do get purple, but what you get is twice as much purple, right? 1 bucket of blue paint plus 1 bucket of red paint gets you 2 buckets of purple paint. And that matters because suppose I was thinking about 1 bucket of blue paint plus 2 buckets of red paint. I wouldn't actually get purple. I'd get hot pink, apparently. And I'd get 3 buckets of hot pink. So, you know, you've got to care about, certainly if you're mixing together the colors and you want to know what color you're going to get out the other side, you need to care about weighting. So the averaging that I'm talking about here is weighted. The amounts that you have matter. By analogy, so we can say that if we want to say maybe this is a quaternion, this is a quaternion, you can clearly write this as 2 of these added together. If we say this one is a bit like this quaternion, then this one is clearly going to be like this quaternion, right? It's got a y is equal to 2 in there. This one I've already told you what it does. It's a 180-degree rotation around the y-axis. This one is also a 180-degree rotation around the y-axis. So it sounds what? Exactly the same as this one? Well, there are some differences between these two quaternions, and I'm afraid to say it might actually depend on the video game engine that you're using. Unity, for example, if you use this one, it will, in addition to rotating 180 around the y-axis, it'll scale the thing up slightly. But there are some video game engines that don't do things that way. Unity is actually, in that respect, doing things a bit wrong, I would say. But anyway, if you're worried about that kind of thing, you can use normalization. If you normalize 2 buckets of purple paint, you get 1 bucket of purple paint. Similarly, if you normalize this quaternion, you get this quaternion. All right. The identity quaternion, which does a 0-degree rotation. Very important quaternion here. Looks like this. We're bringing in some W for the first time. All of these just did 180s, but we've got W on its own. Everything else is equal to 0. What do we think this might do to our 3D model? The answer is, it leaves it alone. It's like, I start out with my cow, and I apply my quaternion to it, and I get my cow again. All right? Because it's doing nothing, there's no axis to speak of. I mean, what does it mean to say that this has an axis? And if you convert it to a matrix, if you've never heard of matrices, don't worry, but if you convert this quaternion to a matrix, you'll get the 3x3 identity matrix or the 4x4 identity matrix if you're using that kind of matrix. And you can also think of this quaternion as essentially being 1, right? Because if you multiply something by 1, you get the thing that you started out with. Similarly, if you multiply any quaternion by this quaternion, you get the quaternion that you started out with. All right. Let's do something powerful. We're going to take a quaternion. This is the identity quaternion, which I've scaled down a little bit, but that's not actually affecting anything. I've got some amount of the identity quaternion, and I'm going to add it to some amount of 180-degree rotation around the z-axis. You don't need me to show you that with my hands. So we're going to get this one, clearly. We're just doing w plus w gets you this w, and then z plus z gets you this z. What's this going to do to our 3D model? The answer is, it's a 90-degree rotation. Hooray, we finally got a rotation by an amount other than 180 degrees. And that kind of makes sense, right? Because we averaged this rotation, and that got us that rotation, a 180 around an axis between them. If you average then a 180 with the 0-degree rotation, well, it makes sense that you'd get a rotation by an amount that's somewhere in between 0 degrees and 180 degrees. In this case, it's 90 degrees because you've got equal amounts of W and the other thing. And you can visualize that as the z-axis again, but this time it's got an arrow going 90 degrees around it instead of 180. All right, here's another quaternion, and it's a funny one, but you saw me say it to you at the beginning. This is, we call it the -1 quaternion, and in a game engine it'll be represented with just w is equal to -1. What's this going to do to our 3D model? Well, maybe you already know. It leaves it alone, right, which sounds a heck of a lot like this quaternion that we just saw. I mean, God, man, that sounds so boring. Like, this quaternion was boring enough on its own. It does nothing. And then this one, you're telling me what? We've got 2 quaternions that do nothing? No, this quaternion is not exactly doing nothing. What it's doing is a 360-degree rotation, right? It's doing this. The cow remains in the same place, but it has gone on a journey in some sense. And that's really important. If you watch my GDC lecture, I go into how this is important for animation, because sometimes you end up with characters, their hands go the wrong way. Doesn't matter. All right. So to really hammer that home, if you've got 2 quaternions like, well, if you've got the same quaternion and you multiply it by itself, so 180 around the y-axis, 180 around the y-axis, if you've got this particular quaternion, multiply it by itself, you get a 360-degree turn. So you could say it's a 360-degree turn around the y-axis, but a 360-degree turn around any axis is always the same thing. It's always this one particular quaternion. And for the sake of completeness, here's the 0-degree, not the 0-degree, that's exactly what I didn't want to say. This is the 0 quaternion. If you have everything equal to 0, it'll like sort of annihilate, right? It'll get rid of your 3D model. It'll send everything to the origin. You can think of this as the 0 matrix, or the number 0, because it sends everything to 0. I just bring it up because I don't want you to mix it up with the identity. The identity is the 0-degree rotation. This is not the 0-degree rotation. This is the get rid of it. All right. Okay. So, part 1b. Dual quaternions. Let's move away from the origin. I've kind of got enough time. So, yeah, we don't want to just think about rotations around the origin, which is what quaternions do. We've got to use dual quaternions. Well, yeah, we want to use dual quaternions. Dual quaternions turn out to be very similar to ordinary quaternions. They've got the W part in there unchanged. The W is still telling you how much identity you've got in your dual quaternion. An ordinary quaternion has an axis that is a line through the origin, and that axis goes straight into the dual quaternion unchanged. But a dual quaternion has a little bit more, as you can see. So, if you want an axis somewhere other than the origin, you need a few more numbers to describe it, and it turns out that 6 does the trick very well. Yeah, so you need these 6 floats. And then this last one is about, it sort of controls screwiness. It's like about taking a rotation and turning it into a rotation and translation. Not going to go into too much detail about that. I do in the GDC lecture. So I want to explain a certain new kind of line to you, though. So I say that the dual quaternions, they can represent a line anywhere. And there's a certain special kind of line that's a bit hard to get your head around, but it's very, very useful, it turns out. So this is the horizon line, which is a line that you've looked at all your life. it is a proper line, and the dual quaternions can represent this line. You might be compelled to say that, oh, the horizon line is more like a circle, but no, if you look at it wherever you go, it's always a line. It's always a straight line from your point of view. Another example of a line like this is sort of the Milky Way in this rather beautiful picture. This is the Milky Way is in some sense extremely far away, right? We're talking about a line here that's so far away that when you look at it and you move yourself around, it doesn't appear to change its position from your point of view. All right, and let me try to give a reason why we might want to care about quaternions as opposed to using vectors for everything. Here I've got a random pattern of dots. I promise that they're random. People sometimes get suspicious. They really are random. Here we've got the same random pattern of dots, and I'm going to lay them on top of each other very, very carefully. All right. And you're going to see, when I do this, once again, the same random pattern of dots. Very, very, very boring. But now I'm going to move it, all right? I'm going to perturb it slightly. So we get, oh, did I move it in a special place? No, let me move it again. Oh. It's always circles. You're seeing circles that are going around some point that we've got here. That's because when I perturb this thing, I'm doing a Euclidean transformation. I'm not squashing or stretching or morphing it in any way. I'm doing a Euclidean transformation. And we're talking about 2D here. A 2D Euclidean transformation is always something that preserves a certain point, right? There's an optical illusion going on. Like if I make it go really far, it sort of disappears. Like here, right now, the circles are getting smaller and smaller, and they're getting bigger and bigger. But here, I can make them small, and then it disappears. It's still a rotation around this point here, but yes, it's just a way for your eyes to see it. But there's a funny trick that you can do with this. All right, so I'm going to start out with the center of rotation here, and I'm going to do a move that's going to cause it to end up over here, all right? I'm going to kind of rock it from side to side. I want you to, and we're going to think about what happens in between, all right? So, here we go. Oh. No, sorry. So, the circles are somehow going off on one side, and they're coming back on the other side. We seeing? Oh, let's see. Bit easier if I can see it. All right. All right. Whoop. They go off on one side, and they come back on the other side. Two things to say about this. Number one, okay, we're starting out like this. It goes on like that. Then it comes back on the other side. But there's an intermediate stage here where suddenly it's stopped being a rotation and it's briefly become a translation, right? It's kind of like the circles here that you see have become straight lines. And that's kind of like saying that the circles have become infinitely big, right? Joan's going to be talking about this kind of thing later a lot. Yeah, and that's a strange thing to say, but it's true. A translation, which is a mathematician's way of saying a movement, a translation is a rotation around a point that's very, very far away. Okay. Another thing to say about this, like, wouldn't it be a shame if someone were to say, do you know what, all rotations are rotations around the origin? If you want to rotate around somewhere, you should translate to this wonderful place called the origin. You should rotate there, and then you should translate back. Terrible idea. It's really denying yourself some very beautiful mathematics. We don't want to do that. We don't want to be scrubs. All right. Another way of illustrating the same thing. Let me see how much time I've got. Yeah, it's okay. So here I've got a Lego motorbike, right? Let me show, and I've attached some poles to its axles. Here's a fun thing you can do. If I put this Lego motorbike down like this, with the handlebars turned very far, it turns out that if I push the motorbike back and forth, it is performing a rotation around a point here. It's performing a rotation, well, take it from me. It's performing a rotation around the place where its two axle lines cross each other. If I turn the handlebars a bit less, it should still perform a rotation around this place where I've got my finger. So it's like if you were going around a roundabout or a traffic circle, as they say in the US, the center of the traffic circle would be here, that you're going around with your handlebars turned like this. Let's ask the dangerous question that now, though. What if the handlebars are completely like this? What if it's parallel? Well, obviously you know what the motorbike does. The motorbike will just go back and forth. It's not doing a rotation, it's doing a translation. What's happened to the place where the axles crossed? Well, it's gone very, very far away, and you can kind of see where it goes, all right? If I bring that close, I've got a picture illustrating this just in case, but yeah, you can. I'm holding them parallel, but you can kind of see that somewhere back there, right, the lines are meeting each other. All right. So here we've got them meeting at this point over here, and this motorbike performs a rotation around this line. Here, if you extend these lines, they meet at a point on the horizon, and the motorbike, when it goes forward, it's doing not a rotation, and certainly not around a line, because it can't go all the way around that line, but it's doing a transformation that preserves that line. Another way of looking at the same thing, here we've got a carousel, and I want you to look at the poles in this carousel. They're all clearly going around this central spindle of the carousel. Over here, you've got a bunch of trees that are behaving quite a lot like the poles, and they're sort of, in a sense, going around the sun, right? Okay. To overlay those, here we've got the motorbike going around the carousel. Here we've got the motorbike going around the sun, in some sense. And one last thing here. So one reason that people in the games industry care a lot about dual quaternions is that they solve this bug, which is called the candy wrapper effect, because it's kind of like this woman's skin is like a balloon or something like that. This woman was animated using 4x4 matrices, which is a terrible thing to use for animation. This woman's arm was animated using dual quaternions, nice dual quaternions, and Blender, Houdini, 3D Studio Max, and Maya all give you the option nowadays to use dual quaternions if you want to. In order to apply them, you have to use something called the exponential and logarithm functions. And at Imagination Technologies, our GPUs are way better than anybody else's GPUs, because we can do this thing called sync, which feeds into exponential and logarithm and speeds them up a little bit. Yes, so Imagination GPUs, they're just the best. All right, so part 2, making things from reflections. Okay, good. I'm not doing too badly for time. So, we want to think about reflections a lot. Projective geometric algebra, or specifically Euclidean plane-based geometric algebra, is a wonderful way of thinking about reflections and solving lots of problems in video games. And reflections tend to start with planes. And one kind of video game where you care a lot about planes is a snowboarding video game, right? If you were programming a video game about snowboarding, you would care a hell of a lot about where is the plane defined by the board and where is the plane defined by the snow, especially if you're about to land on the snow, right? You might want to care about, where do I put the marking on the snow where the player landed? How do I check whether the player should tumble over, this kind of thing? You care a lot about those planes, and that's got to motivate us, because we're going to think about planes a lot, right? So here's how we represent a plane in most game engines. I think all game engines, right? So we've got an x part, a y part, a z part, and a d part. The d part is in some sense displacement from the origin, but we're going to leave it as 0 for now. We've actually got an interesting way of thinking about displacement from the origin. But yes, this plane, we can say that this is like its normal vector. That's what they tend to say. The x part, the y part, and the z part is the normal vector of the plane, and you can indeed visualize it this way. How about this plane? Well, this plane has got the normal vector, but the normal vector is extended. And actually, it's describing the same plane. This plane has got the same normal... it's not got the same normal vector as this plane, but it's facing in the same direction as this plane. So this does multiplying this by 2 does nothing, which should remind you a lot of quaternions, right? This is what we mean by homogeneous representation. Okay, so you can kind of forget about the normal vectors. You kind of want to think of these as just being the plane, in the same way that you think about x, y, z, w as being just the quaternion. All right. Here we've got our basis planes, x plane, y plane, z plane. This is the plane whose normal is in the x direction. Points on it have x equal to 0, which is a bit confusing, I know. Terribly sorry about that, but it's the way it is. Points on this plane have x is equal to 0, and the plane is described by x is equal to 1. Yeah, sorry, you just got to get used to it. This plane is the plane whose normal is in the y direction. Points on it have y is equal to 0. Here's the z plane, and points on it have z is equal to 0. These also get called E1, E2, and E3 in geometric algebra. In fact, by everybody else that you'll hear from this week. But yeah, but I'm video games, so X, Y, Z. All right, there's another kind of plane that we want to think about, though, which is this plane. All right, what's this? We've got X, Y, Z is equal to 0, so this is somehow a plane that isn't facing in any direction? That's a bit weird. But it's D is equal to 1, so it's somehow displaced from the origin? Ugh, what's that plane? Well, the answer is that that plane, if you're a video game developer at least, it's essentially your skybox, all right? Or rather, it is the sky. That's a bit of a simplification, temporary simplification, but this does pretty well. And you might notice that this thing isn't a plane. Right, it's a sphere. It's not a plane. But in this context, we're talking about a sphere that's so big, right? It's so big that it's behaving like a plane, all right? What is the sky? The sky is kind of like a big sphere that surrounds you, but it's a sphere that's so big that if you went up to it and measured how curved it is, you'd find that it isn't curved at all, all right? It's a sphere that's become like or like a circle that's become like a line, like in the thing that I showed you earlier. If we represent planes in this way, then mixing and weighted averaging is still addition, right? This is very, very nice. If you have two planes, you add them together, certainly if they've got the same amounts going on, then you'll get the plane that's directly in between them. All right. Planar reflections at an angle allow us to construct line reflections. Now we're getting into some more interesting maths. So, planar reflections means reflections in a plane, and if you've got a plane, if you've got some x, y, z, d, then that means that you can perform, you've got all the information that you need to perform this reflection. All right, but there's another kind of reflection in this world that you might not have seen. This is a very interesting thing, I would say. There's no camera, there's no screen here. This is actually a reflection. This is called a true mirror. And you might notice that this hand over here, it's a left hand, right, like this. And the other hand is, oh, it's gone. Well, it's also a left hand, which is a bit weird in comparison with ordinary mirrors, because your left hand becomes a right hand, or a left-handed glove becomes a right-handed glove. So, what's going on here is that there are actually two mirrors. You've got an ordinary mirror on this side, and that's an ordinary reflection of this hand, and you've got an ordinary mirror on this side, and that's an ordinary reflection of this hand. But what you see here is, we would say, a two reflection, a perfect two reflection, or a pure two reflection. Yeah. Turns out that a two reflection is a 180-degree turn around the line. You can't see the line in these pictures because they've really, really carefully hidden it. But there is a line there, and it's performing a 180-degree rotation. Your thing and your reflected copy of your thing is rotated 180 degrees. And that should remind you of something, right? We spent ages talking about 180-degree rotations. This is a 180-degree rotation around the y-axis. You can represent this with a quaternion, all right, or a dual quaternion. Here is a hotel room that I was in where they've kind of gone for this effect, but they didn't quite get it right? You see two copies of me. And I want to compare these side by side. So here you've got a line, and this line is a 180-degree turn. It's a line reflection is another way of saying it. The mirrors are at a perfect right angle, And if you represent it as a dual quaternion, you've got a line part and you have no identity part, right? It's like a, it's one of these perfect 180-degree turns. With the one that we've got over here, well, the two that we've got over here, because there are two reflections of me, this one is kind of like a 175-degree turn, and this one is a sort of minus 175-degree turn going the other way. And so if you represent these as dual quaternions, then they've got a little bit of identity in them, right? Because it's not quite a 180. Yeah, and you might notice the little minus sign is the only difference between these two. And also, by the way, these are inverses of one another. So inverting something is just taking a minus sign. That's very, very nice if you're a game developer. All right. The composition of reflections in two planes can be a translation if the planes are parallel. Stephen's already talked about this a bit, but let's make it very explicit for our purposes. So here's my hand. I'm going to do a reflection in this plane followed by a reflection in this plane, all right? Reflect and reflect, all right? We reflected here and then we reflected here. These are at right angles to one another. Reflect and reflect. And that is a 180-degree turn. That's what I've just spent ages talking to you about, right? But this is a way that you can kind of prove it to yourself as many times as you need. All right, what if we were doing reflections in parallel mirrors? Well, in this case, we get, I reflect, and then I reflect again. And I've gone from here to here. That's a translation, right? Nice. Here's a movie, because I like movies. Oh, I like movies and video games. I don't like algebra. Oh, don't know how you can sit and watch algebra for so long. You know, this is a great movie. Don't know how anybody could dislike this movie. So you've got Leonardo DiCaprio with a mirror behind him and in front of him. All right, what are we seeing here? We're seeing, initially, we've got some mirrors that are at an angle to one another, because if you continue these mirrors, you find that they meet at some specific place that Leonardo DiCaprio could walk up to if he wanted to. And that means that the reflections of Leonardo DiCaprio are rotated, right? Because the mirrors are at an angle. Here you've got the mirrors being parallel, and if you continue out these lines, well, they don't meet each other unless you say that they meet at infinity. They're parallel mirrors, so the reflections of Leonardo DiCaprio are translated. All right, and the place that you see this put to work, by the way, with parallel mirrors is a periscope. A periscope has the effect of taking whatever's above the submarine and bringing it down to the level where the person is looking at it, and it does that using parallel mirrors to translate it downwards. Okay, point reflections. What's a point reflection? Well, suppose we start out with our line reflection, our true mirror here, and we put in another reflection plane, and it's at a perfect right angle to this line. What will we get? We get something that's a bit like this. Quite a beautiful object, in my opinion. I've got one of these up here, by the way, so I've got one of these up here, so if anybody wants to play around with this afterwards, I do recommend it. It's quite uncanny because this reflection of you is always on the other side of this point over here, which is exactly the thing that we're trying to talk about. So here's a kind of a way of looking at a point reflection. I'm sort of cheating here because this is in 2D, and 2D point reflections are a different kind of thing. But yeah. Another place where you see a point reflection is this thing from school. I've heard some giggles, so do you do this in Belgium? Does anybody? Yeah? Okay, I'm seeing some people in the audience. All right. Does anybody have a word for this? Shout out. Does anybody have a word for this at all? Nothing. Okay. I've seen it called the seesaw, and I've seen it called the worm. And it turns out that this is a point reflection. It's got some significance. It's not just something that you do to show the kids in primary school that you're cool. So if you put a point exactly here between these two knuckles of my fingers, you get a point such that if you walk from one fingertip to that point and then you walk out the other side by exactly the same distance, you get to the same fingertip on your other hand. One way of thinking about it, so you start to do this thing, you have your hands like this, so that's clearly a reflection. And then you do that, which is a 180, which is a line reflection, and now these are related to each other by a point reflection. So you can do that, and there it is. All right, you can do this with any other fingertip, if you're doing it right. Okay. Rotoreflections and transflections, what are these? By the way, so, at this point, if you're really interested in video games, you're like, oh my God, please shut up. Can we solve some problems in a video game? I promise these are really important. They are if you want to do that thing with Lara Croft, you've got to think about, well, you've got to use rotoreflections and transflections implicitly. All right, a rotoreflection. A rotoreflection is like when you reflect and you rotate, all right? So the clapping pose is a rotoreflection. The praying pose is a ordinary reflection. Clearly, there's a plane that you could have here, and this hand is related to this hand by an ordinary planar reflection. If I do this, all right, so now it's the case that my hands are related to each other by a point reflection, a point that's in between my two wrists there. A rotoreflection is in some sense in between being a planar reflection and a point reflection. And a transflection is the case of a rotoreflection where you've got a reflection and then a translation, right? And that turns out to be, it's like a mixture of, this one is a mixture of a planar reflection and a point reflection where the point is like here. This one turns out to be a mixture of a planar reflection and a point reflection where the point is at infinity, in the same sort of way that a translation is a translation around a line at infinity, except you can't go all the way around. Goodness me, we've got a lot of interruptions. Okay, there's bye. Yeah, you can visualize this thing with, imagine that there's like a piece of paper in between my two hands, and that's the planar reflection. You've got a point there as well. It's your point reflection. And these two are sort of that mixed together. All right. The general term for a point reflection, planar reflection, rotoreflection, and transflection is a flector, and you can represent a flector with just having that plane and that point in there. All right. So part 2B. How much time do I have? Oh, I'm doing pretty well. So, angles, distances, projections, intersections, and orthogonal elements. Finally, we're going to solve some problems in a video game. This is the good part. This is the orgasm of usefulness that you've all been waiting for. So, got the case of a plane and a plane. I promised you snowboarding video game. We're going to label our planes as A and B so that we can write things down, because we're going to be role-playing as mathematicians for a moment. We're going to define this thing M, which is A multiplied by B, where multiplication means reflection composition. It means reflect in A and then reflect in B. And you might say, why on earth would I want to do that? Seriously? Why on earth would I want to reflect in A and then reflect in B? Because, the snowboard is not a mirror and the snow is not a mirror. Is this room double booked or something? I don't know. It's double booked. Goodness me. Oh, poor things. Oh well. They've missed out on my wonderful lecture. Okay, reflect in A, then reflect in B. And that'll give you this thing M. What is M? Well, M is, as you all know, it's a rotation around some line. It's specifically a dual quaternion, right? You do, I can't imagine saying more about this. Reflect in A, then reflect in B, you will get a dual quaternion, even though they're both so it's a function that's taken two planes and it's given you a dual quaternion. Suppose that you wanted, though, the line where these two planes intersect with each other. You wanted the line where these two planes intersect with each other, perhaps because you want to put some marking on the ground where the player has hit the ground, right? That's the kind of thing that you'd want to have in a video game. Well, if you want that line, it turns out that that is the line part of this dual quaternion. That's quite nice. And if you want to just have that line part, and you don't care about the other parts of the dual quaternion, you can have a function that just does that. That's the wedge product. Suppose instead that you wanted the angle between these two planes, because maybe you want it to be the case that if the snowboarder hits the ground at a really bad angle, then they're going to tumble over. They're going to lose their race. All right, so you really want that angle because you want to check it against your critical angle that'll cause them to fall over. Turns out that that angle is arctangent 2 of the square root of the sum of the squares of these parts of the dual quaternion and this part of the dual quaternion. And this has come out of nowhere. This is a bit come out of nowhere. But I put to you that it kind of makes sense that this angle would be something to do with the amount of line that's in your dual quaternion and the amount of identity that's in your dual quaternion. So if you've got a rotation by 0 degrees, that's the identity amount, that's the identity. You've got a rotation by 180 degrees. The angle is clearly related to how much of the identity you've got you're mixing in and how much of that 180 that you're mixing in. And arctangent 2 is a function that essentially takes that ratio. All right. We're going to define, once again, m as being a multiplied by b. And it turns out that this still works even if you're talking about two parallel planes, which could happen in your snowboarding game. You might say, oh, well, that's a really unlikely situation. But actually, if you're snowboarding along the ground, then your planes are parallel with one another. In this case, the m will be a translation rather than a rotation. And it's also the case that A and B no longer have an angle to speak of. Instead, they have a distance. And suppose that you wanted that distance because, yeah, you want to know how far off the ground they are, maybe. Turns out that that's this formula. If this is checking like, okay, if there's an angle, then they have an angle and they don't have a distance. Whereas if they have a distance, then it's this. It's, again, a ratio of the amount of line in there to the amount of identity in there. You might even want the line of intersection of two planes that are parallel, which is a line at infinity. Once again, this will be the line part of your dual quaternion. All right. Some of those formulas were a bit gnarly. We're going to introduce some shorthand notation that will actually clarify things a bit. If you want to extract points, lines, planes, and their amounts, so the amount of point reflection that you've got inside of a rotoreflection, for example, yeah, this notation will be helpful. So, for a reflector or dual quaternion M, so M could be, M could be like this, or it could be like this, either of those two transformations. The shorthand notation for extracting things uses the grade. I just saw poor Joan yawning right now because yeah, like you've actually already heard about the grade, but yeah, so we're video game developers, we're too thick, right? We really need it spelled out. So the grade 1 part of M is a plane, the grade 2 part of M is a line, and the grade 3 part of M is a point. All because, well, how do you make a line? You make a line by intersecting two, or maybe more. You make a line by intersecting two planes. You make a point by intersecting three planes, and you make a plane by having a plane, I guess, right? A plane is one plane. How about the identity? Well, the identity is a reflection in 0 planes, so it kind of makes sense that we would write the identity part of M this way. And then the grade 4 part of M turns out to be the screwiness of M. So this is, Stephen's sort of already gone through this, but if I have a reflection and then another reflection, that'll do me a rotation. If I do further reflection and another reflection and in parallel planes that are both orthogonal to the axis of my rotation, then I'll have a translation as well. So reflect, reflect, and reflect, reflect. That's 4 reflections. And that's what gets you the screw motion. To hammer this home, in this picture I was showing you, talking about the rotoreflection. My hands are related to each other when I'm doing this by a rotoreflection. The plane part of the rotoreflection is written this way. The point part of the rotoreflection is written this way. If you're looking at things in a more code style of way, then okay, we've got a quaternion. Suppose that I only want the line part of my quaternion. I can put some angle brackets around it and say, okay, I want this 2 here, and that'll give me another quaternion. And note that its line part is exactly the same as the line part of this quaternion. And its identity part has now been set to 0 over here, because we're selecting out specifically the grade 2 part of the quaternion, which is the line part. If If you want only the identity part of the quaternion, then you've got a 0 down here. Here we've got a quaternion that's resulting from this, which has an identity part but no line part. All right. The amount of point, line, or plane reflection inside M notation looks something like this. So here we're saying, okay, let's say n was equal to 3, then we'd be asking for the 3 reflection part of M, which is the point part of M. Oh, yeah, sorry. We'd be asking for the orthogonal 3 reflection part of M, which is the point reflection part of M. So if n is 3, and we have a little circle down here, what this means is the amount of point at infinity that's inside of M. If you're talking about something that isn't at infinity, then you have a little filled circle over here. So if you've got a point reflection that isn't at infinity, you want to know your amount of point reflection that isn't at infinity that's inside of M, then that would be the grade 3 part of M, and then with these two bars here in this filled circle. And some people use this notation instead. Okay, I've got to wrap up. All right, back to video games. Plane line. You got you're intersecting the sniper with the plane. It turns out that you've got the line is represented as the line part of a dual quaternion. The plane is represented as a plane. You define M equals A over B. M is going to be a rotoreflection or a transflection. The intersection of that line and that plane is the grade 3 part of M, and that works even if A and B are parallel to one another. It'll be a point at infinity, which is quite useful. By the way, like division and multiplication, it sounds weird, but they're the same sort of thing. It's just that the only difference is that you might have a minus sign in there. You've got point. You've got maybe you want to get the angle between your line and your plane. That turns out to be this formula. The distance between your line and your plane. They'll only have a distance if they're parallel to one another. Will be this formula. So you've got to check for the angle again. And again, it's a ratio of the amount of point and the amount of plane that's in there. Plane point, here we've got a video game where you're going around on the surface of a spaceship and you care a lot about the plane that the player is standing on. You care about the player's position. Maybe we're going to label these as A and B because that's been a useful thing to do in the past. We're going to define M equals A over B, which is reflect in A and then reflect in B, or rather reflect in reflect in B, but maybe sort of going the other way in some sense. That will if you want the line that your player rotates around when you push on the joystick, then that is, it turns out, the grade 2 part of M. It's a very nice thing to have, right? If you're thinking about a point in a plane and you want to project your point onto your plane for some reason, that turns out to be the grade 2 part of M divided by A. If you want the distance between your point and your plane, then that turns out to be this formula again. It's the ratio of the amount of screwiness inside of M and the amount of line that's inside of M. And you can also ask this question, is the point to the left or to the right, or is it embedded inside of the plane? And that turns out to be just the sign of the screwiness of M. So if this is a negative number, then it's on the left. If it's a positive number, on the right. If it's 0, then it's embedded inside the plane. Or possibly vice versa. All right, line and a point. Lara Croft, she's jumped. She's wanting to grab onto that branch. We're going to model the branch as a line and her hand as a point. We're going to define M equals A over B. Maybe we want to know where she's going to grab the branch. The projection of B onto A is this. Maybe we want that distance. The distance is, again, this ratio. Line. We've got some lightsabers. We're going to model them with the middle 6 floats of a dual quaternion because that gives you any arbitrary line. We define M equals A over B. It turns out that the angle is this and the distance is this. Wrapping up. Angle and distance from anything to anything. These are always ratios of amounts of transformations inside of a transformation. And this looks a bit gnarly, but for what it does, it's quite elegant. You can give it any, A and B can be any point, line, or plane. And for any point, line, or plane, this always works. And this is a version, it's basically the same, but it's a bit more fast and compatible with more situations. All right, and as a reminder, all of our code can be deduced from, I guess this is the most important part, of course, so I need the extra volume. All of our code can be deduced from these planes squaring to 1. Why do they square to 1? Because if you reflect and reflect back, that's the identity. This plane, which is the plane at infinity, squares to 0. and you can't reflect and reflect back past the plane to infinity. That's meaningless. Same as you can't go around all the way around a line that's a line at infinity. And with that, it remains to thank the many, many people who have made it so that I can give this presentation. Here's how you can contact me. I'd love to talk to anybody who's interested in this about this kind of thing. And you can also, this is a website where I've set up something where you can play around with these objects. Thank you very much for listening. And I saw Stephen going like this, but from my point of view, I still have 3 minutes left, which is not bad, considering that I extracted, this comes from 2 lectures that I condensed into 1. Anyway, okay. Oh. Thank you so much.
During this GAME mini event, geometric algebra mini event, every lecturer, after he or she did the job, receives a bottle and is taken out of the auditory to radio newsroom to get being interviewed by journalism students,
Right.
digital art students, dangerous technicians.
Wonderful. Sounds like a lot of fun.
We start when he gives a signal, because there's some delay between the sound when the streaming starts.
You don't steal.
Okay, so it is an absolute honor to introduce Joan Lazenby. She is the professor signal processing at Cambridge University. She's also my favorite professor of all time. And you might know her in the game development business because she is also the woman behind Fabric, which is sort of a rather famous inverse kinematic solver that works really well, and that is definitely something that at some point you'll want to take a look at, and of course is also completely based on geometric algebra. So today she'll be talking about conformal transformations, and she will bend the lines and the planes that we've been reflecting into. But I'll let her do all of the talking, of course. So Joan, take it away.
Thank you, Stephen. Is this okay? It's not really loud like Hamish's last few lines. Good, well, thank you, and it's a pleasure to be here. I couldn't be here at the last Game 2020 because I had to teach, but two of my students came. So if you look back on the videos for Game 2020, you'll see some of their work. Good job Hamish is gone because he doesn't like algebra, and I've got quite a lot of algebra, so we'll see. Right, so as Stephen said, I'm going to talk about, let's see if this works. Yeah, so that's another title page. But let's have a look at what we know so far. So we first heard Stephen and Martin talking about the basics of geometric algebra without really specifying the metric of the underlying space. So then Stephen talked about PGA, so the plane-based geometric algebra. So we saw that for graphics, you have a four-dimensional algebra, and you can reflect, and you can translate, and you can rotate really easily, intersect in this algebra. So what am I going to talk about? Well, I'm going to talk about conformal geometric algebra. This is a 5D representation of 3D Euclidean space. And it contains null structures like the PGA. So first of all, I'm going to outline what this is. Then I'm going to say, well, how do we view PGA as a subset of CGA? Then look at some applications, including, as Stephen said, inverse kinematics. And then look perhaps at whether it is sometimes useful to work in a hyperbolic or spherical space. Okay, and there will be quite a lot of algebra in this. Okay, so let's look at conformal geometric algebra, which I'll just call CGA. I'm going to look at the properties of it, transformations in this algebra, blades in this algebra, intersections and reflections, and how to generate other geometries. Now, some of this you will recognize from the PGA. It's very similar. Now, historically, this CGA model was on the last few pages of David Hessner's book in 1984 or so, and none of us actually ever took any notice of it. It was only till 1999, and some people weren't born then, some of us were, that David Hessner, who is the father of geometric algebra, brought this to our attention. And we all went, oh, well, this is interesting. So for many years, we worked on conformal geometric algebra. And then sort of PGA came in because it's not as computation expensive, and I can do many things that CGA can do. But it's good to know about CGA. One of the important things in the conformal algebra is it's covariant. Okay, so the structure of equations and relationships have to remain invariant under my allowed transformations. So basically, if I operate and then transform, I want it to be the same as transforming and then operating. Now, in purely practical terms, what this means, well, one of the things it means is you can prove things really easily, because you can prove things at the origin, and you can rotate and translate off, and it holds for all space. One good thing about this, but generally it's nice to have covariant systems, especially in physics. Okay, so we're going to move to 5D. You've seen that we've had PGA, where we have three vectors which square to 1, and one vector which squares to 0. Now in CGA, so I'm going to inhabit a 5-dimensional space, and it's basically a Euclidean space with there it is, yes, with 2 additional vectors. So I'm going to add on an E and an E bar. So I'll get E1, E2, E3, E and E bar. And E is going to square to 1. E bar is going to square to -1. They're all orthogonal. Okay? So I've got this nice set of orthogonal basis vectors with squares of 1 and -1. Now, before that, if you want to actually find out more details, there's Stephen has a page of CGA resources on BivectorNet, and he has some very nice demonstrations on what you can do with CGA. He also has a cheat sheet somewhere, I thought, but it's not up here. So there are these various resources that you can take a look at. Okay, so I've got no null basis vector, but I have a null structure because I can create 2 new vectors. I'll call them n infinity and n0. One is E plus E bar, one is effectively E minus E bar. There's a half in there. They both, you can multiply them out, the geometric product, just as you've been taught, and they square to 0. Okay, now let's map vectors in Euclidean space. So x is my vector in Euclidean space. I'm going to map it to this big X, which lives in conformal space. I'll call it f of little x, by this expression here. So effectively, I've got the x plus something which squares to 0, but I've added it on this quadratic term. Now, it's not hard to show. If you have all the tools now to multiply that out, x times x, and show it's null. So you can just do that. It's very easy. As long as you understand the geometric product and you know n squared is equal to n naught squared is equal to 0, you can see the null structure, these null points. Now, it may seem like a bit of an odd thing to do, but if I wanted to give you even more maths, I could show you that it's a form of stereographic projection. This comes from a stereographic projection idea. Okay, now if you go back and read some of those resources, you'll see a little difference in notation. Notation has changed over the years. N, you'll see some places n, and that's equivalent to n infinity, and some places you'll see n bar, which is minus 2n naught. X becomes this mapping if I use n bar. Okay, so that's just to note. It doesn't really matter. The advantage of using n naught is if x equals 0, f of x is n naught. It's not minus a half n naught. Okay. So later we'll see that when I talk about inversions, I can invert n naught to give me n infinity, and vice versa. So we call n naught, as I said, is the origin, so n infinity is a point at infinity. So effectively, I'm adding on 2 extra vectors. I'm not just adding on one point at infinity, I'm adding on an origin and a point at infinity. So from now on, I'm just going to drop the infinity for simplicity. I'm just going to put n, but it is n infinity. Now, just following on from what Stephen was saying in his talk, that this is a homogeneous system. Effectively, I've taken an algebra G PQ, gone to G P plus 1, Q plus 1. 3 dimensions, P is 3, Q is 0. And all those null vectors in that space, given by that mapping I had, and just a K, will map to my Euclidean point X. So it's a homogeneous system in that sense. However, I do need to impose a normalization. If I'm actually working with it in practice, in the computer, one needs a normalization. So if I ask that my f of x dot n is minus 1, that's what takes that factor to a half. Now, one thing that there's a whole field called distance geometry. And Stephen also talked about definitions of geometries in terms of distances between points. One nice feature of this is that if I dot, this is a inner product, as you've seen, 2 conformal points together, okay, you can multiply all those out, and you can verify that it's proportional, the result is proportional to the distance between the points. So the inner product recovers distances. And if I take that and say, okay, well, what's x dot x? That is, so a point has 0 distance between itself, so it must be null. So I've recovered the null property via this distance geometry argument. Okay, so in 5D, of course, I would have, you've heard about grades now. So I've got a grade 0, I've got one scalar. I've got a grade my grade 1 objects are vectors, so I've got 5 vectors. I've got, so bivectors, I've got ways of choosing 2 out of 5, which is 10 bivectors. I've got trivectors, I've got ways of choosing 3 out of 5, which is 10 trivectors. I've got 5 4 vectors and 1 pseudoscalar. So I've got 32 elements. So immediately, I've got an algebra, unless I'm very clever, I've got an algebra inside my computer, which when I do the multiplications, is going to be quite time-consuming, okay? Now, there are ways of masking things, but that's one of the reasons that for many plain, line, etc. based manipulations, it's much better to go to PGA. Right, so let's look at transformations. Now, what I'm going to do is just go quickly through transformations, pretty much the transformations that we've seen before. Rotations. Now, you haven't quite seen this, but rotations are in geometric algebra are the exponentials of bivectors. Sorry, rotors. Now, when I'm doing a spatial rotation, I'm just going to use the bivectors, which are the things that you've seen already. And Hamish has just spent ages talking about basically IJK, so E1, E2, E2, E3, E3, E1. They're the basis bivectors, spatial bivectors. So I'm only going to use those. So they're my rotors. So if I rotate, when I apply these rotors, I do a double-sided R something R reverse, which is exactly the same as the quaternion that Hamish was talking about, the quaternion operation. Then you don't have to, again, you could expand all this out. Spatial rotations leave the point at infinity and the origin invariant. So it gives me this equation, because, as I say, the origin and the point at infinity don't change under spatial rotations. So that means if I rotate a point x, translate them to conformal space, the same rotation takes one to the other. Okay? So rotors are exactly the same as in 3D space. How about translations? Okay, translations. Because I've got 10 bivectors, I've got a whole heap of exponentials of bivectors to play around with. So I've got the spatial rotations, so that's done the EIEJ bivectors. So how about the n times a bivectors, where a is just an ordinary spatial vector. So if I take the exponential of something like that, I expand it via a Taylor series, all second order and larger terms are 0 because n squared is 0, and I get 1 plus NA over 2. And again, I translate the point at infinity, it isn't going to change. So you can do the same thing. You can operate on a conformal vector, R reverse, multiply it all out, use the properties, and you see that if I translate in Euclidean space, take those to conformal space, that rotor that I've just put down there will do the translation. And that's exactly the same as PGA, except I'm working in a higher space. Okay. So for those of you who were here for Hamish's and who know about dual quaternions, you can see a similarity between dual quaternions. So I've been looking for these rotors that leave the point at infinity invariant. Okay, Rn, R twiddles is n, and that is the group of Euclidean transformations. So this is a Kleinian, if I'm looking at a Kleinian view of geometry, as Stephen spoke about, then this is what I'd get Euclidean geometry as being looking for transformations which keep n invariant. So let's return to transformations in a minute. Let's just look at incidence relations and blades. Now, you don't need to know much about projective geometry, but can we use the ideas from that in terms of incidence relations in the CGA? So if I have x1 wedge, now this is a wedge, it's the outer product, dots and wedges. I haven't, because these are points. I'll explain a little bit more about why I'm making that point later. x1, wedge x2, etc., wedge xn, and they're all conformal vectors. Now, depending what space I'm in, if I apply a rotor R, this thing R reverse, then it's not hard to show that you can take the R's into each of the X's. And similarly, if I reflect in E, we know that sandwiching something between elements does a reflection, then I can take the E's in. So that means if it holds for a particular case, it holds for a transformed case. So again, I can use this to prove lots of identities, etc. Okay, so now let's just have a quick look at lines and planes. I won't prove why this is the case, but a line L between points A and B, we've seen lots of lines today in slightly different scenarios, is A wedge B wedge N. It's a trivector, okay? Not quite the same as in PGA, because I've moved a dimension up. So any point lying on the line is X, then L wedge X will be 0. And X squared is 0. A plane passing through points A, B, and C is A wedge B wedge C wedge N. It's a 4 vector. And X wedge phi is the equation of a plane. Much easier than writing down the equation of a plane, or you give me 3 points and I do a plane, etc. So it is the case, as people have said, that is a very easy system to work with. So lines trivectors, planes are 4 vectors. A line segment between 2 points A and B is just A wedge B. It's a point pair. Now, point pairs, there's lots of things to say about point pairs, but if you look in the various resources, you can look there if you're interested. Okay, now just to make, I'm working in a space where my points, my Euclidean points are mapped to conformal points. So that's why I've been saying if I want to intersect a blade, say WR, could be a plane, it could be a line, and WS, I want X wedge WR equals 0 and X wedge WS equals 0, because I want it to lie on both of them. Now, you can show that that means that this quantity here, so I take the geometric product and project out a particular grade, take the dual is just multiplying by the pseudoscalar, is the intersection. Now, I'm writing my intersections as the V. That's because I'm using, effectively, the point representation rather than the plane representation. So I'll come back to that. So let's just have a look at CGA versus PGA. So really interesting historical development of this. The origins of, well, I was going to say plane-based, but actually Charles Gunn called it projective geometric algebra. And lots of references, and Stephen and Charles gave the SIGGRAPH course in 2019. So it's been around quite a long time, but it's only quite recently that I think we've all begun to understand it. So PGA is a subset of CGA. And from what we've seen so far, seems so PGA can actually do everything CGA can, but actually I'm going up to CGA because, why? Well, why? Because I've got 32 elements in my algebra, so it's more complicated. But we'll have a look in a minute. If you want to understand this a bit more, there's some good, it sort of starts with Anthony actually writing something in a book that Leo and I edited, which was quite good, which is talking about, you know, how one might explain Charles Gunn's approach. He had 2 spaces at that time. Chris has written a blog post, which is nice, and Leo and Stephen have a guided tour to plane-based geometric algebra, which sort of says, which also gives the kind of relationship. But let me summarize it, basically, because it's fairly quick to do. Let me take a point in Euclidean space, so let me call it x1, e1 plus x2, e2 plus x3, e3. Map that to conformal space, so it's my normal mapping. In 4D PGA, that x there becomes a plane. And if any of you have seen the cheat sheets here, you'll have seen that that's what it, put that there in case I trip over it. That's what it is. And I take the dual of that, and I get the point plus E naught, a specific type of dual. Now, if I take my point, which I've called x5 to show it's in conformal space, I wedge it with n, take the minus sign, multiply it by I5, the pseudoscalar in my CGA, and I take the same thing, x5 wedge n, dot it with n naught, I get the PGA. So that's telling me quite a lot. So it's telling me that if I want to do this mapping down, oops, sorry. Yeah. If I want to do that mapping, what this gives me is precisely the PGA, except the E naught is replaced by N. Okay, so N is fine, it's my E naught. The dual here, sorry, yeah, N and E naught, but the dual gives me the N naught. So the element that squares to 0 in when I project down from CJ is N naught, which isn't so good. But it is comparable, if you read some of the PJ literature, this reciprocal ER naught, which squares to 0 and dots with E naught to give 1, is very similar to N naught in the CGA. So it's here where in the PGA, the choice to work with planes is kind of made for us. Because although my N and my N naught square to 0 and behave the same way in regards dotting with the basis vectors, it's only this second form, this first form rather, with the N in it, that transforms properly as a point under all Euclidean rotors, particularly translations. Okay, so it's kind of, this was a learning curve for me to understand, you know, how you got from CGA to PGA. Okay, so I do need to now say, well, what's the point of this? What do I gain from actually adding on an extra dimension and increasing my space from 16 to 32? And if we're dealing with lines, planes, etc., you know, you use PGA. So however, if we do go to CJ, I can now include circles and spheres as blades, and I can get dilations and inversions, and therefore special conformal transformations as rotors, i.e. e to the exponential of a bivector. And the ability to work in non-Euclidean spaces is really quite well defined. Okay, so there's some of the advantages. So let's quickly go through those. Again, you don't need to understand the details of this, but if I want to dilate, as Stephen was saying, we sometimes want to scale things. So a dilation about the origin, I could write it as x goes to a factor times x. If I write that factor as e to the minus alpha, so a factor beta, then let me take a rotor as e to the alpha over 2 e bar. So I'm taking one of these bivectors that we haven't used so far. We've used E1, E2, etc., and we've used N, E1, and E2. We haven't used these. So what do these give? So these, if I sandwich my conformal point between this rotor, I multiply it all out, what I find is it actually does a dilation. This x hat here is the dilated x. So you've got enough information to multiply all that out, but basically, rotors, dilations are now rotors. So I've expanded my list of transformations that will work. Inversions. So we've seen that sandwiching between things is really important. I mean, the whole of PJ was motivated by reflecting in things. Reflections are really important everywhere. But turns out inversions, so that x goes to 1 over x, is done by reflecting in E. Taking a minus sign. So again, you can multiply it all out, and you can see that it gives me an inversion. Now, I don't know whether anyone has ever looked at a book on inversive geometry or books on inversive geometry. It's really tough. And it's quite tough it's okay, not too bad in 2 dimensions. Try going to 3 dimensions. It's horrendous, really. With this, it's identical. It's absolutely identical. You're just using the same constructions to do the operations. One slide on special conformal transformations, because I don't think you'll come, certainly in graphics, I don't think you come across them very much. But special conformal transformations are things like this, quite weird things. And in GA, it's actually formed by a concatenation of rotors and reflections. So a translation rotor and a reflection, translation, reflection. Okay, so it does the whole of special conformal transformations, although we don't need to worry too much. Okay, so that's one. We've got these transformations. Now, circles and spheres. This is lovely because I am totally incapable of working conventionally with circles and spheres now. If someone says to me, right, I'll give you 3 points, say lie on a circle, so A, B, C, or 3 points, say lie on a sphere, 4 points, lie on a sphere. Give me the equation of that circle or that sphere. I don't think I can do it conventionally, basically, because it's so easy using this. The circle is A wedge B wedge C. The sphere is A wedge B wedge C wedge D. And the equation would be X wedge C equals 0 and X wedge sigma equals 0. They're the equations of my circle and sphere. So extremely useful. So I've got my primitives. I've got a line P wedge Q wedge N, or a point pair P wedge Q. I've got a plane P wedge Q wedge R wedge N. I've got a circle P wedge Q wedge R, and I've got a sphere P wedge Q wedge R wedge S. All very easy. So I've gained the ability to do circles and spheres. Of course, if I can't do ellipses, or I can't do conics. And if you look at the literature, there's quite a lot of people who've gone to higher order algebras in order to get the ability to do conics. Except, I think 5 is enough for me at the moment. Just note here that a line is a circle passing through the point at infinity, precisely as we think, and a plane is a sphere passing through the point at infinity. So precisely what we might think. Now, just one really nice thing is this reflection again. If I take M, A, M, I'm reflecting the object A in the object M. And sometimes we've seen a lot of reflecting in planes. But suppose I reflect the point at infinity, N, in my circle or my sphere. Well, what can it give, really? It's pretty much got to give the center. So if you give me 3 points, you give me 4 points that lie on a sphere, I move them to CGA, I reflect the point at infinity in my sphere, and I've got the center of my sphere. It is really nice. Very easy to prove all this, because as I say, you prove it at the origin for a simple case, then you can translate and rotate it off. Okay, duality. Just let me make a point about duality. I'm working in a CJ where I've chosen that X is my point. I could work in the dual space where my Y, my X star, where X star is X times I5, is a sphere. Okay? In PJ, we've seen that we've been guided to use the plane, the representation of points as planes. And as I said before, basically that's because I believe that if I rotate my dual, it's not the same as rotating the point and taking the dual for some rotors. Okay, so the duals are really nice because spheres, I can have my sphere, which is my A wedge, B wedge, C wedge, D. I can take the dual of it, and my dual is, of course, this is a 4 blade, so this is a 1. It's grade 1, so I have the center minus a factor of n, where rho is a radius. So I can immediately give you the radius and the center. Lines are the same as in PJ pretty much. I take the dual and I get a 3 vector, so this is a bivector. And the M is the direction of the line and A is a point on the line. Circles, very similar to spheres. I take the dual, I get the center minus a multiple of n, which gives me the radius. Now, when I'm taking that dual, it's the plane with respect to the plane the circle is in. And the dual planes, again, will encode the normal to the plane and the distance of the plane from the origin. So really, the lines and the planes, you get exactly the same thing in PGA. The circles and the spheres are particular to CGA. Okay, so how about applications? As Stephen said, so this is back in 2011, and it was part of Andreas Aristidou's PhD thesis. So he was working in CGA, because PGA didn't quite exist then. It sort of existed, but we were not aware of its benefits. So the idea is you have a lot of linked arms, elements, or whatever, rods. So, I say I want to move my linkage so that P4, this end effector, goes to this target point here. This is a really simple idea. It was programmed up totally in CGA. I'll tell you why in a minute. So the idea is that you basically say, okay, if my point is at P4, I'll draw a line between P2 and P4, and I'll intersect it with the sphere that is the right distance for the length of the P3-4 element. So you just keep doing that up the chain. And you get to here, and you go the other way. So that's why it was forward and backward, reaching inverse kinematics. It's incredibly quick. And, okay, so it's not, I could do this without CJ, but everything was programmed up as lines and points, and we had spheres, so it was very easy to do. But where it really was beneficial was imposing constraints. Okay, because lots of joints have constraints. Andreas programmed up whole bodies, etc., with all intricate constraints. If my joint angles at P3 are such that I'm only allowed a certain range of angles, I've got a cone. So that means I've got a circle effectively. So I can implement all my constraints if I'm in CGA, by looking at the closest point, from closest point on a circle to a point, closest point on a sphere to a point, etc. All of these intersections were really easy to implement. And I think it would have been a bit of a nightmare in trying to do all this conventionally. But of course, possible. So that was the, so if I, hopefully, let me see if this plays. This was a really one of the first. It's not very happy, is it? Oh, why has it done that? Okay. At least I made it. Normally VLC is pretty reliable. It's not playing ball, is it? Ah, there we go. For some reason, I don't know why. So basically, this was it was a first go at hand. He had in some of those. I wanted to make it loop. Hang on. So your hand is an extremely constrained linkage. So you can't move various joints past a few degrees, etc. So it was interesting to see where you could put the end effectors and how you could constrain everything so it did the best it can. The good thing about this algorithm, one of the things that was not programmed into it from the beginning, is that it almost never fails. It actually does the best job it can, but it almost never fails. Let's go back to. Now, we've just seen a little bit, we've seen a bit in Stephen's talk, and then we saw Hamish doing it again, that he was taking his line to his point and things like this. And this is an example of transforming between objects. So can I find a rotor, and that's what he was doing, to take me from object 1 to object 2? And effectively, again, and this ties in with what Stephen was talking about, if I consider the average object, x1 plus x2, and I reflect x1 in it, then I should get x2, more or less. And I do, modulo a factor. So I get a factor. Now my factor is, in this CJ, is a scalar plus a 4 vector. That's okay. So that is my rotor. Basically, you give me a sphere, 2 spheres, and they don't even have to be the same size. I can give you a rotor that takes one to the other. Okay, 2 circles. So what you can do, therefore, if I got the rotor, that's e to the bivector, I can interpolate that bivector so I can have a very smooth transition from one object to another. So this is some of Hugo's taking one of the blue circles to the blue circle and interpolating it, a point pair to a longer point pair, a line to a line. So things like that, actually also quite hard to do conventionally. And then, using that same idea, we can interpolate objects. So I just said that if I reflect in this average, I get, reflect x1, I get x2. And these x1, x2, via this argument, I can project it down into something which is the same nature as x1 and x2. That means, so you give me x1 and x2, they can be circles, they can be spheres, etc. I can take alpha x1 plus 1 minus alpha x2, so I'm just adding them, and project down to something which is the same nature as x1 and x2. So I can add lines, planes, circles, spheres, and it's very fast. So this is slightly different. This is this direct interpolation, alpha x1 plus 1 minus alpha x2. And Hugo, this is Hugo's PhD thesis, he has actually used this in some architecture applications where he's averaged objects to cluster them, which is quite an interesting thing to do. It worked really quite well. Okay, now generating of the geometries. We said that one of the key features of Euclidean geometry and what we were doing in CJ was leaving n invariant. So what do we get by insisting on something else being left invariant? And again, it's alluded to on the cheat sheets. We've got what you would do for spherical hyperbolic, and Stephen mentioned it. In conformal J, I'd leave E bar invariant to give me spherical geometry, and I'd leave E invariant to give me hyperbolic geometry. Okay, so hyperbolic geometry. What do I do? I mean, how do I kind of do this? Then, I mean, what we did is we found the form of the translation rotor, which kept E invariant, then defined an origin and translated it to get the form of the point. Now, the form of the point is like this, and there's a lambda in it, which is a length scale, a fundamental length scale. Sorry, I meant that's our mapping in hyperbolic space. Oh, it's an interesting, when we first saw this, we kind of thought, oh, interesting, that our original CJ mapping was not dimensionally correct. So, but this is dimensionally correct. So let's see if this one works. Now this is an old, I might have the same problem with this, but we'll check. Oh, this time it worked. Okay, so Stephen mentioned that programming in hyperbolic geometry or spherical geometry is exactly the same as doing anything else. So you define your points, you define I want it to rotate and translate around, you just move all the points by rotors, because we know what the rotors are. So this is the enterprise moving in hyperbolic space. And it's the same as, this is how you program up normal movements. Now, spherical geometry is quite interesting. Spherical keeps E bar invariant, which means I've got a space with a Euclidean signature. It's plus, 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 plus. And that may have many advantages. Now, lambda is related to the curvature of my space. So as lambda goes to infinity, I get a flat Euclidean space. And take my word for it, the spherical, I think this first appeared in a paper of Antony's in, I can't remember where it was, but this was mapping a Euclidean point to spherical space with this lambda in. And I moved back to Euclidean space quite easily. But I've got a lambda. Now, why is it useful to work in this space? Well, maybe. Oh, this is just these are the translation rotors in spherical space. That's what they look like. But so we don't need to worry too much about that. Rotation rotors are the same as in all the other space, e to the spatial bivector. Now, it seems like a pretty big step to work in a curved space. So what can it give us? Well, one problem with both PJ and CJ that we don't really encounter when we're just moving things around, you know, I'm doing operations, moving things around, is that I'm not optimizing normally. I've got no cost functions. I'm not trying to set up cost functions. If I do try to do that, these null structures really mess things around. I don't get nice surfaces, basically. So it's not a nice, they're not particularly nice spaces to have like big optimization problems in. Sphericals, however, is quite a nice, at the cost of having a lambda floating around, it's quite a nice, well-behaved Euclidean metric. So what would be an example of using this? Well, how about finding optimal rotation and translation together? So this is some of Alberto's work, another PhD student. And what he's done is he's, I don't know, some of you may have heard of the PoseNet type, well, it is PoseNet. You basically have a camera going through, you get ground truth data, you have something which tells you the ground truth orientation and translation of the camera, either relative to an inertial frame or relative to the previous frame. And you take pictures, basically. And you want to train a neural network to predict, from the pictures, to predict the rotation and translation of the camera. Well, it's great. I mean, it works quite well. So PoseNet is, and there's all variations on PoseNet, but oh my goodness, the cost functions, because rotation and translation are such different things, are horrendous. Well, they're not horrendous, but they're quite involved. And there's lots of papers which have come out having better cost functions. So Alberto tried basically camera position orientation for all our training data. You shove it up into spherical space, and then you've got the pose. So you've got a motor, you've got this motor in spherical space. These are constrained, some of these constrained, of course. Then, why don't we input our labels and just change PoseNet? So instead of change the cost function, keep the architecture, change the cost function, and change what it's predicting, and it seems to work really well. So actually, it seems to be quite a nice space for whatever the network is doing. It's actually finding that it's a nice space to work in. Now, of course, one could try in other optimization problems predicting rotation and translation accurately. You might say, excuse me, what's lambda? Because I can't put lambda, I can't put a symbolic lambda into a neural network. Well, we just found that lambda, we scale lambda according to the scale of our data. We pick a lambda, 100 or something, and we scale our data to be in a certain box, and it works pretty well. So here's the same thing. This should work, hopefully. This was from way back. There's Rich Wareham. This is the Enterprise moving a spherical space. Exactly the same. Rotation rotors are the same, and the translation rotors were was that given by that expression I just had up. So it doesn't take much more time to program up than it would in Euclidean space. Okay, so what have I've done? So I've tried to describe mapping from a PQ space to a P+1 Q+1 space to get conformal geometric algebra. So that lines, planes, circles, spheres are blades, points are null vectors. Rotations, translations, inversions, dilations are rotations, are rotors and reflections in CGA. The approach is covariant. A spherical space with Euclidean signature might actually, I'm beginning to think, be really useful in some cases. Now, I'm wondering, is it possible to program in an environment, because these things are so similar, where I have a 4-1 space, so 4 positive vectors, one negative squaring vector, such that I can move down to PGA, or I can move down to spherical space as my application dictates. Because, there are certain things that you wouldn't go to CGA if you want to intersect planes, basically, or, move planes around, lines around. But sometimes having spheres, especially in graphics, bounding spheres, etc., is actually really important. So, you know, I'm wondering if if it's possible to have this overarching, this sort of tree where we can go from one algebra to another. Yeah, conics, we go even to a higher dimensional algebra, but I haven't really played around with that. Good, that's it, thank you. Is that it for the, am I the last? Oh, oh, Chris is in here. Oh, I'll miss some of Chris's. Oh. Right.
Hello?
All right. The last talk for today is Chris Doran. Doran. And he is the author, the main author of Geometric Algebra for Physicists. So he is a very hardcore physicist. Together, of course, with Anthony Lazenby, but he made me say it, Anthony. He hasn't just done physics, he is also the creator of the Enlighten global illumination system that you might know from the Frostbite engine and many other engines, Unity too. So the global illumination system based on spherical harmonics. That is his responsibility, was his company. And today he'll be giving a talk about high-performance geometric algebra.
Oh, thank you, Stephen. Hope this okay. Yep, good. Yeah, I think when I originally pitched this talk, I called it 5 tricks for high-performance geometric algebra. But I've got a little bit carried away in the last few days writing it, so it's increased. I had one last night, so it increased again. Yeah, a little bit of background about me. So I haven't been attending GA conferences for a little while. I took a sort of break, but I'm kind of back now. I've been researching geometric algebra for quite a long time now. I started back in 1990. I started my PhD, and yeah, it's on. Okay. Yeah. Is it not loud enough? Do you want me to shout? I think I attended my first geometric algebra conference in 1991 in Poland, along with David Hestenes and Stephen Anthony. One of the key things that I sort of say to people now, the sort of lesson from my own research time, was pick a problem to work on first. Don't say I'm going to do research into geometric algebra. I get asked that quite a lot of the time. People say they want to come work with me to research geometric algebra. Kind of doesn't mean anything. Pick a problem, pick an algebra that's going to be useful for it, and use that to help you solve your problem. Around 2004, 2005, I was getting a little bit frustrated with life in academia, so I span out a company called GMRX that went on to work on this global illumination problem in the games industry. We got a solution running for computing the bounce light in real time in a 3D world, which originally ran on PlayStation 3, which kind of at the time was thought to be pretty much impossible. By 2012, we had the same solution running on an iPhone, so we were doing global illumination on an iPhone. And this was something that people thought was the domain of extremely big ray tracing farms. So to see it done a completely different way on such small hardware was quite revolutionary. That Enlightened software, as I say, found its way into, it became the main global real-time GI solution for Unity. It was a lot of our customers using the Unreal Engine. It became the standard in Frostbite, so all of the Electronic Arts games use it, still do use it actually. And it was used in hundreds of games in the end. But in the end, we were acquired by Arm. It's the way the industry works. Small companies get acquired by big companies. Big companies then generally mess up what was good about the small companies, and the technology kind of dissolves. But a bunch of the team is still there, and some of the team have actually moved on with me to work on a couple of new projects. I left Arm in 2018 and have spent most of the last few years mixing research with advising some new startups. And there's 2 companies I'm spending most of my time with at the moment that might be of interest to some people here. The first one is Monumo, who are kindly sponsoring a lot of my work on GA at the moment. This is a new Cambridge-based startup. We are applying AI techniques to design more efficient electric motors, predominantly focused on EVs, but also pretty much anywhere you see motors, generators. We want to come up with some far, far better designs than is currently possible. And a key step in that is having extremely fast simulations, which is where we're using GA in our toolchain at the moment. So we can simulate the electromagnetic fields very fast, and that gives us a handle on how to design more efficient motors. And if you look at how motors are designed currently, it's a few engineers sit in front of some Autodesk products, something like that. And they can churn through a few designs a day because it takes a long time to get the results out. We're now churning through hundreds of thousands of simulations and then using AI to help us drive those simulations in directions of more promising designs. So that's very exciting and not surprisingly is a hot topic for investors, so it's going pretty well. The second company is an interesting one. They approached me from Cardiff, but not from the main sort of technical university in Cardiff. They approached me from the art university, as it were. Actually, it's the one where a lot of games developers learn. A team there have developed a proposal for replacing projective geometry in the graphics pipeline. If you've played around with the graphics pipeline, you'll know that it's got projective geometry is kind of baked into the way the thing works. And that basically means that once your field of view gets above about 100 degrees, you start getting distortions at the edges. So you're actually limited to quite a narrow field of view. What Fovotech have developed is a way of opening up the field of view so that you can get to about 150 degree field of view without those nasty distortion effects. You can get some really interesting, good-looking images. And you can do that still in real time. They've got it implemented in Unreal and Unity at the moment. So that's getting a lot of interest, partly from games, actually more from sort of architectural visualization spaces and film CGI. But the effects are quite stunning. If you play a first-person shooter with this turned on, after a while you kind of get used to it. And then when you turn it off, it's like you've got tunnel vision, that you're stuck with this very, very narrow field of view. You want to get everything back. So I think it could be a really interesting next step in gaming. I hope, anyway. I'm currently, my own research topics are, along with the stuff of these companies, discrete geometric calculus. This is something I've talked about at conferences for years. I wanted other people to develop it. They haven't, so I'm having to do it myself. But it's what we're starting to use inside Monumo. And when I left academia, gauge theory gravity was kind of my thing with Anthony. So I'm back doing that now. It's nice to come back to. It's like going back to an old girlfriend, I suppose. So I knew I was the last talk, and I knew that today was going to be a very, very dense program where a lot of information has been thrown at you. So I was trying to figure out how I can tell you something useful, given that pretty much everyone here has seen too much and is probably quite tired. So I'm going to tell you some stuff that I would not normally show, because I want you to forget about it as soon as you've seen it, because it's largely useless. At least this first bit is, but it at least makes a point that is relevant for optimization and some of the thought processes I've been through for optimizing stuff. So we've done lots of stuff about the geometry of the objects we can create inside geometric algebra. This is a little bit more on the algebraic side. So how do we actually kind of write algorithms that can do these manipulations as optimally as possible? So we'll just start with a very, very simple little thought experiment, just given our 2D algebra. So 2D algebra has got scalar 1, 2 vectors, E1 and E2, and its bivector E1, E2. And the one thing, hopefully, you've learned so far today is that E1, E2 squares to -1. It's like an imaginary number. Now, as soon as you have an algebra with objects that square to 1 that aren't the identity, immediately something should start sort of triggering in your mind that there are some interesting things you can do with that. In particular, you can define projection operations like P plus and P minus here. So I'm going to pick out E1, because E1 squared is 1, because it's a vector, unit vector. And if you define P plus and P minus, so P plus, for example, is a half 1 plus E1. If you square that, you get a quarter 1 plus E1 all squared. Expand it out, you get 1 plus 2E1 plus E1 squared, which is 1. And you get back to P plus. So you get something that squares to itself. If it squares to itself, that means a number of things. First of all, it can't have an inverse. Because if it did, you could multiply through by that and prove that the thing was 1, which it isn't. So we're starting to get these things as non-invertible, which is obviously going to happen in geometric algebra, because there are only certain algebras where everything's invertible. And if you look at, say, P plus times P minus, you get 1 plus E1 times 1 minus E1, which difference of 2 squares is 1 minus E1 squared, which is 0. So these two things annihilate each other. That's the really interesting point. It means that you can define things in your algebra that when you multiply them together, you get 0. And that gives us an optimization trick. This is the way I'll think about it at the moment. This is a sort of optimization trick. Then we'll come back to what this means. We can take an arbitrary object, and we can use the fact that P plus plus P minus is 1 to just put two factors of 1 on either side, and then decompose the object down into these four terms. So again, it's pure algebra. There's no geometry here. And by the way, actually, this thing of adding a scalar to a vector, I'm quickly going to ditch that as being useless. But if we look inside that sort of sandwich with one of these projection operators on either side, you see that only a certain number of things survive. So E1 times P plus is P plus, so you can drop all the E1 terms, you just get a scalar out. And if you put, say, an E2 between two P pluses, that annihilates, you get 0. And similarly, an E1, E2 in there gives you 0. And when you kind of track through that, you see that given an arbitrary A, there are 4 numbers that you can sit inside one in each of those 4 sandwich possibilities, which are slightly suggestively labeled A11, A12, A21, and A22. Same for B. Obviously, this all looks horribly ugly. There's no reason to actually do this. But now we're going to multiply these things together. So remember, in this case, A and B are completely arbitrary elements, multivectors in this 4D algebra. So multiplying together 2 things with 4 terms in each. So there should be 16 multiplications to do. Okay? But when we put these together and use the fact that some of these P pluses and P minuses are 0, you find that actually you only get 8 multiplications to do. And we've discovered something. We've actually invented a new type of product here. If I put my A's and B's into this funny structure here and multiply them together where the rows of A multiply the columns of B, you get exactly the correct terms. Only 8 multiplications to do, and we get this quite compact representations. So obviously what we've done here is we've rediscovered matrices. They're a kind of optimization trick for doing geometric algebra calculations. That's kind of how I like to think about matrices. And we've also, as a byproduct, constructed the standard matrix representation for G20. So this doesn't sound particularly impressive, but actually, factors of 2 matter in a lot of code, particularly if you're trying to write anything optimal. And if you're trying to multiply together general geometric algebra elements, you need to sort of take care of this. But also, part of the reason I want to talk about this, it was partly inspired by, I think, Stephen's original poster about getting rid of matrices, is if we actually look at the historical timeline, matrices aren't that old. Matrices were introduced in the 1850s by that guy, Cayley, the multiplication table is named after. And Clifford introduced his algebras only 30 years later. And also, the 1850s was also the time that Hamilton was introducing the quaternions. So they were all kind of in the mixture at the same time. It wasn't the case that matrices came first and then everything was built on top of them. Interestingly, something I didn't know until recently is that Cayley had just been appointed a new professor of maths at Cambridge just when Clifford arrived there as an undergraduate. So Clifford attended Cayley's lectures. And unfortunately, Joan's not here now. She was telling me over lunch that in the Trinity Library, they've got records of letters that Clifford wrote to Cayley. So obviously they all knew each other. But it kind of begs a really interesting question that I like to ask about maths quite often. What if this chronology had been reversed? Clifford didn't need Cayley's matrices to come up with his algebra. If the timelines been slightly different, we could easily have had geometric algebra first and matrices second. And then we'd be asking, well, how do you construct matrices in terms of geometric algebras? We wouldn't be thinking so much, well, how do we construct geometric algebras in terms of matrices, which is the way it's often presented. I talk about this quite a lot when I talk about geometric algebra to sixth formers, people sort of preparing to come to university. I like to give the talk about G20 and motivating complex numbers. And it's all you need to do to motivate complex numbers is have this idea that orthogonal vectors anti-commute. That's all it takes. And it's not actually a big step to imagine that we could have got to complex numbers via that route before we got to them via solving quadratic equations. Because actually, how often do you really need to solve a quadratic equation? It's not that exciting a problem. But dealing with geometry in 2D and 3D is something that engineers and people were really focused on. So I do think a lot of the chronology of math is a lot more accidental than we realize. But we always kind of teach math as this logical progression from reals to complexes, etc., all based on the historical timeline for when things were discovered. Anyway, so that's just an aside. It turns out this is a result partly due to Cayley. Every associative algebra, so every geometric algebra, has a matrix representation. And in the sort of mid-20th century, somebody sat down and worked them all out for every possible geometric algebra, every possible Clifford algebra. And this is the basic table. We only need to, I'll explain in the next slide why we need to go up to total size 8. But on here, there's some interesting cases to look at. This M means a matrix of size 16 or 8 or 4. And then the thing in the brackets is matrix over real, matrix over complex. Or, rather curiously, we get these matrices over quaternions. That's actually a little bit surprising in some sense. It's not how we typically do representation theory in maths. Usually we work over reals and complexes, and we treat quaternions as sort of two-dimensional complex matrices. But they're absolutely baked into geometric algebra. You see quaternions all over the place. Some sort of notable ones here, 2 by 2, G20, the 2D is 2 by 2 real matrices. 3D, the Pauli algebra was mentioned before lunch, is 2 by 2 complex matrices. Space-time algebra is actually 2 by 2 matrices over quaternions. And the conformal, so 4, 1, is P plus Q is 5, 3, it's 4 by 4 matrices over complex numbers. And if you want to go and implement a geometric algebra computation, you can use this. Okay, so this is the point where you can now forget about all this stuff, because this particular table itself, it's sort of interesting, but it's not the key to writing optimal code. But it is useful to know. Here's a quick summary of some of the results there. Other things to point out, the matrices are always powers of 2 because the total number of elements in the algebra is always a power of 2. The even dimensional ones are always over the reals or quaternions. The balanced one, these ones down the middle, which are sort of particularly interesting, they are always matrices over the reals, and they just kind of get bigger and bigger. In odd dimensions, the representation depends on the square of the pseudoscalar. If the pseudoscalar squares to -1, you get a representation of complexes. If it squares to +1, you get a pair of real representations. And actually, those pairs of real ones are kind of nice because there's some computational efficiency there. One other thing to mention, in the pure maths literature, when people talk about something called a spinor, they're imagining those matrices acting on a column vector of some particular size. That is one way to think about spinors. It's kind of the old-fashioned way. It's not how we tend to think about spinors in geometric algebra. What's really interesting, though, I think much more interesting than those matrix representations, are the relationships between algebras. There are ways to jump from one algebra to another. And this is kind of one of the messages I want to kind of bring home to people. Don't fixate on working on one particular algebra. You should learn how they all relate to each other. You should learn how to jump between them. There are two particularly useful ways of jumping. One is this thing called the evens or projector split. So the even half of any algebra is a geometric algebra in its own right. And there's this relationship here that tells you that the even subalgebra of PQ can be one of these two. It could be GP minus 1 or GPQ minus 1, depending how you do the split. Similarly, you can split you can use what's called a conformal split, where the algebra, say, GP plus 1, Q plus 1, is the product of the algebra GPQ and G11. This was what David talked about briefly in the paper that he published, in his book, actually, that we all kind of missed for about 20 years. And if you track all of this through, you find that you can remove multiples of 8 from every algebra, and then the big algebra is just 8 by 8 matrices over the smaller ones. That means that, and the fact that GP plus 1, Q plus 1 is 2 by 2 matrices over the smaller one means that for anything larger than 8, you can always figure out the smaller algebra of size less than 8 that the representation is done. So this table has done it all, because all the larger ones you can extrapolate from there. Okay, so what is all this useful? Where is all this useful in actually writing some optimal code? So what these matrices do is they encode this trick that certain things can multiply, can annihilate each other when you multiply them together. So if you're taking general elements, you can't do better than this type of way of multiplying things together. But what we can do, rather than implementing those large matrices, is we can use a trick where we only focus on the even half of an algebra. So we're going to use this even split in particular. First of all, just going to explain exactly how it works, because this also raises another interesting point, and I think sometimes gets forgotten in the field. The way this works is you go into your PQ algebra. Let's say it's all the generator Euclidean, the E1 up to En. And you pick out En, and you multiply all the other n minus 1 generators by that. So you've got a new set of bivectors in this space, capital EI. When you form the symmetric product of those new generators, they also satisfy EIJ plus EJEI is, in case, minus 2 delta IJ. They are generators of a geometric algebra. They anti-commute with each other, and they square to plus 1 or minus 1. And so they generate a new algebra, which is the algebra of the even subalgebra of the large one. And it defines this embedding, in this particular case, G0 n minus 1 is embedded inside Gn0. This is not the kind of the obvious embedding where if you had, say, E1, E2, E3, E4, you just pick out E1, E2, E3 and make them generators. It's a different type of embedding, something that David Tessie's likes to call the projective split. And one thing that's really worth remembering here is that this grade concept that we talk about a lot is actually quite subjective in many cases. In this particular case, these capital EIs, they're grade 2 if we think of them in GPQ, but as generators for, say, GQP minus 1, they're grade 1. Grade depends where the thing is embedded. So sometimes people get a little bit fixated on the types of grade and what the grade means, but grade's a little bit more of a flexible concept than you might think. Okay, so how does this all relate to actual implementation? So there are basically 2 ways you can go about trying to implement geometric algebras numerically. There's the geometric product first way, which is the way I tend to prefer, and there's the kind of inner-outer product first way. The geometric product first way, you really want to implement something like those matrix representations, because if you don't, you're missing all these factors of 2 that you can halve the computation by. That's very good for doing multiplying rotors together, for example. It's less good if you just want to do, say, a vector, an outer product of a vector and another vector giving you a bivector, because you may be doing some wasteful calculation. And actually, this does become unfeasible for larger algebras. It's something else that we kind of don't talk about too much with geometric algebra, but once you get above a certain size, you can't even begin to store these multivectors. If you were looking at, say, a 64-dimensional space, where I could quite happily write with vectors and bivectors in that space, but if you try to write down a rotor in that space and store it, there isn't enough storage in all the compute facilities on the planet. So this is not a good idea for large algebras, but it's a very good idea for small algebras. The other way is you build up a whole library where you store vectors as an object, bivectors as an object, 3 vectors, 4 vectors, and implement all sorts of different product rules between them. Quite painful. But in some sense, that's the only way to do the much larger algebras. So I'm going to talk about ways of doing both of these. And I think the switchover point where the first approach starts to get a bit too slow is around 6 dimensions to 8 dimensions, somewhere around there. When the matrices start getting up to about 8 by 8, you start to worry that there's a bit of computational overhead there. So this is the first of the tricks. When implementing a general geometric algebra and implementing a geometric product first, we're going to use some version of those matrix representations. But what we don't really need to do is implement the entire algebra, because in every practical implementation, you are never going to add an even object to an odd grade object. All of the useful applications have things of a particular grade, so say vectors, bivectors, whatever, or things like rotors, which are all even. But aside from that stuff I did at the start, which is all nonsense, you would never add a scalar to a vector in a useful application. There are 1 or 2 counterexamples. The most relevant counterexample would be the E and B fields, where you do combine them, but actually you shouldn't be in 3D when you're combining them. You should be up in space-time algebra anyway when you're combining them. So we don't need to represent the algebra by its full matrix representation. We just need to get the matrix representation of the even half of it, and we need to define some map between even and odd elements, and then we can implement a much more efficient product. In fact, we implement 4 products, even, odd, odd, even, and odd, odd. So I'll just run through some examples of this. The particular library that I've been working on is all implementing this in Julia. Just out of interest, any Julia programmers here? Okay, I will not talk too much about Julia in that case. I like to try to keep the implementation as sort of clean and simple as possible, which you can do with the geometric product first implementation. So what you do is you just implement a formal multiplication operator. Julia allows you to overload the star operator, so you're not going to do anything other than that. So you need a product, and you need a projection operation. So you need an operation that you can take in a multivector and project out the grade 0, 1, 2, 3, 4 bits of it, whatever. That's already enough to do pretty much everything in geometric algebra. You don't need to implement a separate dot or inner or outer products, because you just take a geometric product and project out the bit you want. What you do also need, though, is some way of getting numbers out of the geometric algebra. So you need the scalar part to return a number rather than a thing inside the geometric algebra. I've overloaded some operations in Julia, so actually I use trace from linear algebra to take out the scalar part. And it's handy to have a separate dot product that takes the scalar part, so it's sort of A-B scalar part projection. And you need reverse. And again, Julia has this nice multiple dispatch thing, so you can overload the tick operator, the adjoint operator in linear algebra. So R tick is R reverse. It means what you can do in Julia, which is a struggle in some other languages, is your code looks very, very much like your handwritten geometric algebra work. You can actually go further in the space-time algebra, for example. The generators are all gammas, and Julia actually typesets them as gammas, which is quite nice. So we we need to implement the even subalgebra of G20, it's the first example. Look at our little table. The even subalgebra is G01, which is a complex numbers, which is exactly what you expect. You're in two-dimensional algebra. You've got scalars and bivectors, a bivector squared to minus 1, so they are complex numbers. Indeed, I think, to me, they genuinely, that is complex numbers. It's not just a representation of that. That's where complex numbers come from. So, under the hood, the implementation is then very simple. For even elements, you just store a complex number. For odd elements, you don't store the odd element. You store E1 times that, because that maps it back to an even element. So you have two types of struct, but they're both got the same things in them, both got complex numbers in them, one for even, one for odd, and you implement the products between them. So even is just a complex multiplication. For odd ones, you've just got to put a star in various places where it's needed. And then reverse for the even is complex conjugation. Reverse for odd doesn't do anything because they're only R vectors, they reverse themselves. And once you've got those operations defined, that's basically it. The rest of it is all the sort of usual fluff that goes around some library code, but implement that and you're basically done with your 2D geometric algebra implementation. And you can just kind of think of it, it's basically a kind of wrapper to make complex numbers more useful, because it includes the ability to do a proper geometric product. G30, this is one where if you implemented the full algebra, you'd be doing Pauli matrices, so complex 2x2 matrices. But by just implementing the even part, you're actually back with quaternions, which is, I think, is more natural anyway for 3D. So your underlying representation for 3D geometry is a quaternion, and for the even elements, and in any odd dimensional space, the map between even and odd is always done by the pseudoscalar, because it's nice and easy to do. So you store minus I3 times your odd elements as a quaternion, and then all you've got to do when you implement the products is put an appropriate minus sign in the product of two odd elements. And that's G30 coded up. And you can start doing some speed tests of this. And actually some of the results are really surprising. It's a really good lesson that just trying to count multiplications is not a good measure of performance on modern hardware. You really need to actually do some proper calculations and just time them. And Julia has very, very nice libraries for timing things. It takes care of a lot of the sort of hard work for figuring out when start and stop times are. So, for example, just doing some timings on this laptop, a floating point multiplication takes 25 nanoseconds on this. A quaternion product takes about 35 nanoseconds. Even though that's doing 60 multiplies compared to 1, it's only a little bit slower than one floating point, because the compiler does clever things with using SIMD, and you're able to sort of store up the calculations. You can take advantage of some latency in there. And a few surprising things here. So in 3D, the sandwich operation, R reverse, to do a rotation, which is quite a few multiplications, and I've always thought is a little bit slow. That whole thing takes 50 nanoseconds. If you go into Julia and code up a 3x3 matrix, let that act on a 3-component vector, that takes 90 nanoseconds. It's actually slower than the sandwich product, which I was very surprised by, because the sandwich product you think should be more complicated. It's certainly got more multiplications in it, but that's not naturally a good measure. Another kind of interesting comparison was the cross product versus multiplying two quaternions and projecting out the bivector part. Because you think, okay, I'm doing more multiplications with the quaternion case, but actually, Q1, Q2, and project out the bivector part is 60 nanoseconds, whereas the cross product was built into Julia was 90 nanoseconds, so slower. Don't really know why. These things are really, they're so deep down in the hardware, you don't really know, but we're getting some nice sort of very, very optimal behavior here. And the really curious thing, and this is something that I think there may even be possible to do better, is that quaternion product takes about 30 nanoseconds. Projecting out the bivector part of it takes another 30 nanoseconds, because the bulk of the time is in allocation. which seems a bit wasteful. I feel like I might be able to do something even better there. Seems odd to take longer to sort of get less numbers out. But this is clearly a good it's a good start for something that's pretty optimal, and it's going to stay optimal for these sort of smaller algebras. So a very pointedly called G40, the projective geometry algebra, because this is the algebra that you would do projective geometry in, and David Hesnes did do projective geometry in when he wrote about it. Joan was doing it for spherical geometry, but it's the four-dimensional Euclidean algebra. It's kind of the algebra of the projective stuff that goes on under the hood in OpenGL and DirectX and that sort of thing. This is quite a nice one to be in, because if we look at the even subalgebra of G40, the pseudoscalar there squares to +1, not -1, so it's not built over the complexes, it's built over 2 copies. And we get, because it's a thing that squares to +1, we get those things I showed at the start, those decomposition projection operations. They work again, and they halve the amount of work further. So actually, in this algebra, the representation is a pair of quaternions, and when you multiply them together, you just multiply each quaternion in its own slot. There's no kind of cross terms to worry about, so it's very efficient. So this projective geometry, like this G40, you end up storing a pair of quaternions for the even elements, and the map from even to odd is this usual projective split, as David Hesnes would call it. And again, this is extremely fast. So again, sort of still way down in the nanoseconds. Next one of interest is G41. So this is the conformal algebra. It's the one that Joan was talking about, and this is the one that has PGA embedded in it. The plane-based geometric algebra is embedded in this. So again, we look at our matrix table. The even subalgebra of G41 is actually G40, and that can be implemented as 2x2 matrices with quaternion entries, which is the way I've done it in the Julia code. And actually, you don't even bother to implement 2x2 matrices. You just unwrap that. Those calculations is much easier. There is a question in my mind about whether this should be implemented as quaternions with 2x2 matrices as coefficients, but I suspect that'll be slower. But I actually do need to do some speed tests on that. So again, this is a very easy one to implement. 2x2 matrices over quaternions, odd dimensions, so the map between even and odd is on the pseudoscalar, which squares to -1 in this case. And because I didn't want to get into any fights about notation, I just labeled the 2 extra dimensions, E4 and F4, E4 squared to +1, F4 squared to -1. And everyone can knock themselves out with their own favorite notation for N and N bar, or E0, or N0, or N infinity, or E infinity, or whatever combination is you prefer. And inside this conformal geometric algebra, we do have this subalgebra of elements built from the E1, E2, E3, the Euclidean vectors, and the point at infinity N. This is the sort of smaller PGA part. So to represent entire CGA, even part we're using 2x2 matrices of quaternions. Obviously, to get to the PGA, then, we just need a pair of quaternions, or a dual quaternion. So for PGA, we can implement this with the even elements given by quaternion pair, a dual quaternion, and the even-odd map, the natural thing to do here is to do that with a I3, the three-dimensional pseudoscalars at E1, E2, E3. The one extra thing we also need to implement in PGA is a dual, the PGA dual, which is this slightly clunky mechanism for enabling you to sort of grab numbers out. But that's actually no effort. It's just a couple of reverses and sign changes inside your element, so it's very fast. And again, so I was doing some more speed checks on this just to check out how PGA, CGA all kind of compare with each other, how G40 compares, and also how they compare with the matrix routine. So inside PGA, we can do a a sandwich, and R reverse, so that would be a transformation of a point or a plane, etc. That takes about 70 nanoseconds, which is fast. And again, compares favorably with the 4x4 matrix acting on a vector, which takes 100 nanoseconds. The product of two rotors in this space, so that's the combination of two dual quaternions to get a new one, is about 30 nanoseconds. No, actually, no slower than doing one quaternion multiply. It's kind of odd. That compares very favorably with about 200 nanoseconds for multiplying two 4x4 matrices together in Julia. Similarly, you can do a projection operation here, so we can look at, say, two planes multiplied together to get the line between them. That's about 60 nanoseconds. If we kind of compare them with CGA, just the fatter algebra, that R reverse sandwich, say 70 nanoseconds in PGA, about 100 nanoseconds in CGA. So going from CGA to PGA is a speed up, but it's maybe not quite the sort of big order of magnitude speed up you might have expected. It's a bit more modest than that. And a rotor-rotor composition in CGA is about 50 nanoseconds compared to 35 nanoseconds. So again, some advantage to PGA, not huge. You can also kind of compare with projective G40, where that wedge product, say intersecting, let's say we're going to intersect two planes to get a line, that's about 60 nanoseconds in PGA, about 30 nanoseconds in projective in G40. So G40 potentially has some advantages in some cases there. Obviously, what you lose in G40 is this very nice feature that rotors in PGA are Euclidean transformations. So if you wanted to do a translation thing, you'd be back using 4x4 matrices in G40. And worth emphasizing, this is a 6-7-year-old Dell laptop, so the absolute timings don't matter a great deal. It's more about the comparison, but these are nanoseconds, right? This is really, really fast stuff. I wasn't sure if we needed a break here, but should I just keep going? I'll keep going. Okay. Couple of other sort of I've implemented a whole bunch of algebras, and one of the nice things that Julia has is a thing called multiple dispatch, where you essentially keep overloading the star operator, and it does, as soon as it sees something times something else, it just looks at all the various instantiations it has for multiplication and does the right thing. This means that you can have all of the algebras in flight at the same time. So there's no reason for your session to be like the way we used to run inside Maple, for example, where at the start you say, right, I'm in the STA, and then everything's done in STA. You can have all the algebras in flight at the same time. You can easily move between CGA, PGA, G40, etc. And if you want to squeeze the last bits of optimization out, you can pick and choose the right one for the right calculation. I don't know if it's possible to do that automatically. Probably with a bit of thought, but certainly you can easily take a CGA expression and think, okay, now I just want to drop into PGA and do that, and vice versa. So hopefully it removes some of the sort of fighting about which algebra is better in some particular cases. I also implemented line geometry. It's one that I quite like, this G33 algebra. It's one where null vectors now represent lines in three-dimensional space, and you can do quite fun stuff with that. And the final question, which I'm going to answer on this slide anyway, on the next slide, if we look at the main algebras of kind of relevance to three-dimensional geometry, we've looked at the three-dimensional Euclidean space, G30, that's implemented with quaternions. We've looked at G40, so projective geometry. That's implemented with a pair of quaternions. We've looked at PGA, implemented with a pair of quaternions. And we've looked at conformal geometric algebra, which is implemented as a 2x2 matrix of quaternions. So I spent a long time advocating to hardware guys that they should try to implement all sorts of geometric algebra stuff in hardware. I completely changed my mind now. All I want the hardware to do is give us quaternion multiplication as fast as possible. Everything else we can take care of. Geometric algebra will organize that into sort of sensible ways. But you just give us the fastest possible quaternion multiply, and we're kind of done. So in any time that you're in conversations with a hardware guy, and they're asking about what they could do to implement geometric algebra efficiently, just tell them that. Just say, just want quaternions. I want to be able to quaternions in as few clock cycles as possible. Hopefully, there's made a lot of them in parallel as well. That'd be nice. Okay, so that's the kind of the core philosophy of this low-level Julia library I've written. But that only does algebras up to 6 or so dimensions. If you want to implement a more general algebra that can go up to much larger dimensions, that's when you have to ditch the matrix representation idea. You need to go back to some way of storing blades and their values. This is something I'd written a long time ago in Haskell. Lots of people have written their own versions of this. In fact, I think for a lot of people, the way you learn geometric algebra is you write your own GA library. It's kind of natural. That's what I encourage people to do. And generally, the way it works in Haskell was your key object is a thing representing the blade and the value. And a multi-vector is just a list of them. Actually, Haskell works with linked lists, which unfortunately is very, very slow. So I wrote some libraries doing this in Haskell. It was only when I started porting them to Julia that I learned how slow this was as an approach. The biggest issue with it in kind of Julia language is that you're working with an array of structs, and that's bad. What you want to be working in with a struct with arrays inside it. That's much more efficient, it's much more hardware friendly, much more parallelizable. So I've been working on implementing the more general case by flipping things to this struct of arrays approach and coming up with a new way of solving the hard part of the problem when you multiply together 2 blades, which is actually getting the sign right. So I'll explain why this was hard and the sort of the solution I've got to this now. So the way I tend to represent the blade, this is a fairly standard trick. I was first shown it by Steve Gall a long time ago, is you can represent a blade by a binary number. For flexibility, we like to implement mixed signature. So we had a scheme where binary number 1 is E1, then the next slot is F1, which is something squares to -1, E2 squares plus 1, F2 squares to -1, and so on. You don't have to do that. If you just want to implement a large Euclidean algebra, you could just make it E1, E2, E3, E4, and so on. But basically, each blade then is just encoded by a binary number. So the really nice thing about that is that when you're multiplying 2 of these blades together, the resultant blade is just an XOR, binary XOR of those 2 numbers, because the only way that a blade can survive is if it's in one and not in the other. The only way a vector can survive is if it's in one and not in the other. So that's really easy. Binary XOR is obviously going to be very fast and easy to implement. The hard part's getting the sign right. If you look at the sign, say, of a product here, on the left we've got E1, E2, F2, E4, on the right got E1, F2, E3, E4, F4, etc. To get the sign, you have to take the E1 on the right, anti-commute it past 3 things on the left, annihilate it with an E1, and keep doing that until you've got everything back in your canonical order, and you've got to count the number of swaps and count the number of times that an F is squared to -1. Now, counting the number of Fs is easy, because you do that with a bit mask. But counting the swaps is actually quite painful. It was particularly painful in Haskell that didn't have any access to underlying binary representations. You actually had to encode, convert everything back to decimal, so which made it particularly slow. But even with the raw access to kind of raw binary operations, there's no simple way of taking these 2 blades and counting the number of swaps when you multiply them together. What we did in our original Maple implementation was use lookup tables, which back in the 90s, that was fine, but these days lookup tables are just a dreadful way of trying to get any kind of performance out, because you've wasted about 30 plus clock cycles just getting this thing from memory. I spent some time when I was at ARM, what kind of kept me interested there was the thought that it might be worth designing circuitry to do this particular computation for you, this counting thing. But then I realized that that's just a spectacularly bad idea for lots of reasons. One of them is this is just not a great way of implementing the small geometric algebras. And secondly, I found a way to do that doesn't involve changing the hardware at all. It just works in existing hardware. So fortunately, ARM didn't waste any time on this. So this is the next trick I want to talk about. This is a slightly different way of encoding blades in a binary representation so that getting the sign of the product is straightforward. And it comes back to this conformal split relation. The idea that the algebra G P plus 1 Q plus 1 is a direct product of G11, which is actually a 2x2 matrix, if you like, and GPQ. This is what David called the conformal split. And this was actually how David introduced conformal geometric algebra in the first place. The way this works is you start off with your EI and FI, little EI, little FI basis vectors, and you introduce these new trivectors. Capital EI is now, say, capital E1 is E1 times ENFN, where EN and FN are the little generators of your conformal bit. Similarly for FI, these capital E's and F's are trivectors, but they still satisfy the correct generator relations. Actually, the EI squared to plus 1, the FI squared to minus 1, and they anti-commute with each other. So they generate a new algebra. They generate the algebra GPQ. And because of the way these are constructed as trivectors, the capital E's commute with everything built from the little e's. So these two algebras now commute with each other. And this is another example of how you need to be a little bit more flexible about grade. So these trivectors, E's and F's, they're grade 3 objects in the large algebra, in what you might think of as the conformal algebra. But in the smaller algebra, they're vectors. So they can be trivectors in one space, vectors in another interpretation. Actually, this makes complete sense geometrically into the conformal geometric algebra, because these trivectors we would think of as lines going from the origin through the point of interest and out to infinity. That's what the trivector represents. So it makes complete sense that when you're trying to go back to the smaller algebra, it's those lines are the generators, they're lines through the origin. That's what we think of when we're doing, say, G30. We tend not to do the split this way anymore. We tend to do the split via an embedding. But this actually was the way David originally thought about it, and there is some advantage to this. The fact that these algebras commute is definitely an advantage. So what I've been doing is using this trick as a way of decomposing the balanced algebra, so GNN, which is quite a good one to implement because it contains everything within it. Using this trick, GNN can be decomposed into a whole set of commuting subalgebras. But the generators have this slightly odd behavior that the generators of the next one are trivectors in the space, and the generators of the next one are 5 vectors in the space, and so on. But each of these little blocks is a copy of G11, and they all commute with each other, and that's a huge advantage, which I haven't seen exploited a great deal up till now. So this gives us a slightly more complicated binary representation of objects, but it's one that's going to give us a great deal of speed up. So now there is the binary number 1 represents E1, and 2 represents F1. But the number 4 doesn't represent E2 anymore. It represents E2 times N1. Number 8 represents F2 times N1, and so on. So it's a slightly more complicated encoding. So if we then want to get the vector F3, that's actually represented by this binary number now. But the big advantage of this is that everything commutes, so that when you've got taking a product of two of these blobs, you can kind of line them up on top of each other, because all the other bits have commuted past each other, and all you have to work out is the correct sign for each of the individual products now. That's a product within this valence algebra. So this is one of those Cayley tables for G11. And what we care about is when do we get a minus sign in this? And you get a minus sign when the first entry contains an F and the second entry is a vector. So that's a much easier thing to implement as a binary test. We want the first term to contain an F, so that just means we take an AND between our first element and 1, 0, 1, 0, 1, 0, 1, 0, etc. And the second term needs to be a vector. And that can be done by shifting left and doing an XOR, and then just seeing if we have a 1 in the second or fourth or so on slot. And then the final thing is you do an AND between that and the first vector, and that, whether that's even or odd, tells you whether you need a plus sign or a minus sign. So all of these are very, very simple binary operations. They're all available for a sort of low-level languages like C and Julia can just implement these. And obviously they're blindingly fast because they're just bitwise operations. And this whole thing, it actually just ends up as being sort of 3 lines of code. So this gives you a route now to implementing the general product of 2 arbitrary elements where the way you store these now is a list of the basis elements that are present in the multivector and a list of the float values. You can go in and you can do the multiplication very, very fast. The problem is addition's a real pain here because you end up with a big set of resulting blades and resulting numbers. But those blades aren't in any canonical order. So you have to do some sorting, and then you have to see whether you've got 2 blades with the same coefficient and add them. And that's the part that is really, really slow. And I haven't got a really good answer for how to do that efficiently at the moment. I'm not sure anyone has. What I do for, say, G44 is I actually just rather crudely temporarily expand to 264 components, add those 2 vectors and sparsify back using a kind of sparse library that Julia has. But it isn't brilliantly fast. For G3232, this is where I'm using 64-bit ints as the representation of the blades. This approach isn't even available, so you just have to do some sorting stuff under the hood. So this does turn out to be quite slow. This is not a good way of implementing geometric algebra for those smaller algebras, the ones that we've kind of been talking about a lot today. But it's not desperately slow. It's still, it's still a few 200 nanoseconds to do a product, so it's perfectly good for most of the applications we want. But it's not the way to really squeeze optimal performance out. So for example, a quaternion multiply, I did this on a different laptop, but 20 to 30 nanoseconds doing it in G30 is a sort of native operation. About 600 nanoseconds if you work in this fat algebra, encode 2 quaternions there and do the multiplication. So it's a fair chunk slower. I think there's still a lot of room for improvement, and this actually how you write this stuff efficiently is still a bit of an open problem. Okay, so I've got 3 tricks so far. I've still got 4 to go, but these 4 are all quite similar, and Joan's already kind of presaged one or 2 of them. These are all to do with rotors, bivectors, exponentials, and so on. I was in a sort of discussion thread recently where people I was talking to did not agree with this approach to implementing geometric algebra because for them, geometric algebra is all about interior products, exterior products, basically kind of Grassmann algebra, if you like. They didn't care about rotors, so they didn't care about these type of optimizations. But I think for most of us, we would, when people say, what's the unique thing that geometric algebra has that nothing else has? It's rotors, exponentials, and bivectors, and so on. That's the real special secret sauce. And actually, in some cases, exponentiation can be quite hard. Stephen, are you going to talk about exponentiation in? Okay, right. Yeah, these can be quite hard to implement. So when I first talked about this library back at the last conference, the request came from the audience was very much you have to implement an exponential operator. So I've implemented an exponential and a bivector exponential operator. But when you get up to things like conformal geometric algebra, this actually gets quite slow. The problem in CGA is you're exponentiating a bivector. This bivector squares to a scalar and a 4 vector. That scalar can be 0 or positive or negative. The 4 vector can also have a square that is 0, positive or negative. You end up with this quite ugly branchy code, lots of if statements. They're generally not a good idea at runtime. If you can avoid them, you're going to get something more optimal. So I was led to this trick that I'd never seen before, but I guess it's probably something that most computer scientists maybe learn. I thought so. So it's surprisingly effective, far more effective than I kind of thought it would be. So if we try to exponentiate the bivector b, what we do is we find the power of 2 so that b divided by that power of 2 has a magnitude less than 1, so that when you exponentiate, you can implement that with a Taylor series. After about 10 terms, you've got something with magnitude less than 1 to the power of 10 divided by 10 factorial. You've got something that's vanishingly small. So you can truncate your series there. So that's just 10 geometric products. That's very quick to do. And then finally, you need to raise the result back to the power of 2 to the n, but that's just multiplying yourself by yourself n times, which is another n multiplications, and not many. And that gets you the result. I was just kind of astonished to see this, because I'd never come across it before. Really, really neat. So I've implemented this in the cases where the product is hard to do via other ways. And certainly by the time up to CGA, this is really good, really effective. And apparently this is actually what's going on under the hood inside your computer when you actually ask it to exponentiate something. It's using a version of this and some other lookup table and stuff and other bits of magic. There's two further tricks that Joan talked about a bit as well, to do with rotors and normalization and the ability to add them and scale them and so on. And there's a particularly useful result that works up to 5 dimensions, which is following. Rotors are even elements. So they're even elements with 2 properties. First one is R reverse is 1, they're normalized to 1. And the second key property is that psi A psi reverse, the sandwich, returns a vector. Now, in general, in larger spaces, that is not guaranteed. But actually, up to 5 dimensions, you can guarantee that psi A psi reverse will give a vector, or RA reverse will be a vector provided R reverse is 1. So you've just got 1 test rather than 2, which is actually quite useful, because that second thing is a very, very hard thing to test in practice. And there's a little proof there that you can check if you want. So that gives us another way of actually our users get a little bit more accuracy out of that numerical exponentiation calculation, that if you have a psi that you hope's a rotor, but it's drifted off a little bit from being a rotor numerically, all you need to do is renormalize it by computing psi psi reverse and then dividing by the square root, or one of the square root of that. Because you're close to 1 anyway in that normalization, that square root you can truncate after 1 term. And this improves the accuracy of that exponential formula even further. It's just using this trick that we use quite a lot, that even elements, once they're normalized, give you back a rotor. And the nice thing is actually, you can go to a mathematical proof and show that that is the correct thing to do. That is the closest rotor to psi, given that you want to get to something that is normalized to 1. Typical application of this is, let's say you're defining some camera motion with keyboard and mouse input. The way I like to do that is each time you kind of press the key or move the mouse, that's a bivector, a conformal bivector, a PGA bivector typically in this case, sent around. You then get a small change to your overall rotor that controls the pose of the camera, which you add in as a 1 plus b to then you multiply that by your rotor at step I. The new rotor is then take that psi, normalize it so you're back to being a pure rotor again, and that gives you the rotor at the next position. That's a really, really fast way of implementing camera control. Similarly, you can use this to get a very fast version of slurp, so a spherical interpolation. You need that to correctly interpolate between two rotors because the path between them is generally a curved path. But you can use a little bit of algebra here to show you that the midpoint rotor between, say, two rotors R1 and R2, in these low-dimensional spaces, you can get just by adding the rotor and then dividing by the magnitude. And that is the correct interpolated, the correct mathematical interpolation of two rotors. They could be rotations, translations, etc. Up to 5D, this implements that very, very efficiently. That gives you the midpoint of the slurp. If you want to do more accurate slurp, you can just do a few more midpoints until eventually you can lerp between them, and then the lerp formula is fine. You just do a linear interpolation and normalize the result. And that gets you a nice smooth path between various pose elements, which is very handy for, say, animations, that sort of thing. And a final one, this is coming back to CGA, conformal geometric algebra, which I actually ended up using quite a lot now, is suppose you're in CGA and you're working in one of the spaces where there's an invariant, whether it's E, E bar, or N. So it could be N if we're in Euclidean space, N would be a null vector. We've got 2 points, X and Y. We want to find the translation between them. Then this T, which is YGXG plus GYGX, is the unnormalized rotor that does it. And the normalization is just a scalar in this case. It's very easy to get, if you even need it. One of the nice things being a homogeneous space, you probably don't care about scalar normalizations quite often. There's a short little proof, and actually this is quite a fun thing to play around with, because once you see that that's the rotor between them, you can go into spherical and hyperbolic and Euclidean space and get the distance between 2 points from the amount of this rotor that goes around. It gives you quite a lot of insight into where the various distance formulae come from. Okay, so I've slightly exceeded my time. Yes, sorry about that. So summary, particularly for people kind of coming into the field, these are the things that I'd like you to think about. Please focus on applications. I really don't want to get any more emails from people saying they want to do GA research with me. I don't even know what that means, actually. Pick a problem and solve it. Don't get stuck in one algebra, and definitely don't get stuck in fights between whether one algebra is better or worse than another algebra. You should be able to understand all of them and pick the one that's appropriate for a particular problem. And you should be able to move between them, and you should write code that enables you to move between them. One of the things that has been a stumbling block for people that hopefully isn't a problem for the sort of next generation coming through, this idea of sum of the vector squaring to 0, sum squaring to +1, sum squared to -1 is a bit weird at first. It's less weird to physicists because we're used to it from special relativity, but that's weird to us when we first meet it as well. So it's weird to everyone. You just kind of have to embrace it. It's just where a lot of the interesting algebras are. They just have this mixed signature space. In fact, I think it's the key thing that Clifford didn't have in his original work that he missed that would have enabled him to go a lot further. That and the fact that he died straight after he put his first paper out. Not much you can do about that. Grade is a flexible concept, so don't get too hung up on whether particular things mean something. They may mean one thing in one algebra or something else in another algebra. It's probably worth learning the matrix representations, but don't fret about them too much. You can just look them up, but just be aware that they kind of exist and there might be some useful information in them. Those tricks I just showed at the end there, they are all part of a kind of standard game developer's toolbox to avoid doing any trig or log or exponential calculations if you absolutely can. Rotors are very, very good for avoiding taking exponentials and so on. Because they avoid working with the Euler angles for say 3x3 rotation matrices. That gives them a lot of performance boost. If you are writing your own code, make it easy to move between algebras. I think this was something that we did wrong in our early implementations. So you want to be able to have multiple algebras in flight simultaneously. And keep your API clean. I think if people just write code where you've implemented a geometric product, a projection, a reverse operation, and a take a scale apart operation, you're kind of done. Just do that as a base layer and then build on top of that. And if there are any hardware guys in the audience, if you talk to any hardware guys, just give us Quaternions. Hardware guy, I've talked to you about Quaternions. You don't need to be told that. Okay, and finally, if you're interested in looking at the code, it's up there. It's still being tested at the moment. It's not, so a couple of little gnarly bugs in it, but welcome to play around with it if you're interested in Julia. I do recommend Julia as a really interesting language to look at. It's very kind of future-proof, I think. Contact details, there is a Twitter handle for the last few remnants of people that still bother with Twitter these days. Thank you to Monumo for allowing me to just do all this stuff on their pay, which is very good of them. And also, yeah, thank you to the organisers for putting this event together.
Okay, this closes the day for today. Also, Chris is sent out with the black box to the newsroom to make it survive. Thank you. And I have some journalist students who will guide you to the newsroom for personal one-to-one interviews and thanks. Yes. Right.
So thanks everybody for being here. And I know you're all dying for more, but you'll have to wait till tomorrow.
Okay, tomorrow is physics.
Yeah, tomorrow is physics and Friday is back to grammar and yes, would like to take it to dinner. Okay. You don't take it? Oh, no, I'll come back. I trust.
test.
I want to check. I want to make sure this works before I shop tomorrow. Is this yours or is this his?
You can use this, yes. Normally I set the
It flashed. There it's got it. Got it. It just took a while.
yes, that's the recording device.
Oh, that could be a problem. The PowerPoint.
Live demos.
No. If it's, I can. We can just put. I've got it on the.
Yes, I think we go for one machine for this presentation.
Yeah.
Just make sure that the font is embedded in the PowerPoint.
That. Say that again.
That the font, the text font, seems to be stable in the PowerPoint. Ja, dat was handig voor op te pakken. Abdullah, is je nog niet wat zijn? When is going to double check whether your signal is copy protected.
Okay.
It's very weird, but we discovered it with Joanne.
Oh.
Like everything went smooth and then she starts and it gets there. Like the machines, they
Okay.
Your creativity is still protected. You'll survive. Ja, Floor, ja, kom eraf morgen. Oh, alles physics, hè. Feel free. I'll do my best. Ja. Het zal wel zware parametrisch. Ja, kwantummechanica, kun je daar vooral niet van lezen. Dus het gewoon kun ik kijken naar het programma. Als dat niet tof is, dan zit ze dan vast. Ik weet niet dat je zegt dat ik ga komen, maar je moet even kijken al
Okay.
Very beautiful laptop.
Well, we could just run it from a different machine.
Yes, but I want to try something.
No.
Ja, ik zal het video ook even belichten wat ik ga gebeuren met deze. Ja.
Is it working?
Not yet. Yep.
Not yet. I mean, would it help if I sent you just my PDF?
Yes, you can.
I don't know. I mean, it didn't record. Well,
You can do it,
Yeah.
but we will see if Steve
Steve, yeah, okay.
has the time to manually do your thing. Hier en lijntjes. That is not yours?
No, it was just sitting.
Got anything left here? I don't think so. Ah, that's my mouse.
There are options I can do with your Mac, but I will not fuck it up. So if it's no problem for you, we will do it on
That'd be fine. In fact, it sounds good. So if you've got the price,
we do it.
we'll do it tomorrow. Okay.
Are you the first speaker?
No. I'm second. Okay.
We're still trying to find a device that can make it go.
Thank you for finding all of those things. Thank you, though. Yes, I think I dare say I got to the important stuff before.
Moet er nog iemand testen of? Ja, ik heb dat nu eerst gezien en dat gebeurt tijdens het event.
Ik weet dat, ja.
Ik heb het nu ook plots gezien.
Ja, dus dat iemand moet komen zeker.
Ik heb dat plots gezien.
De Gerdy van dienst, ja, ik heb het ook nu plots gezien. Want ik sta hier geregeld in die zaal. Dus, Ja, Florian.